Good morning, everybody. My name is Chris Bean, and I'm the head of the geophysics section here at the Dublin Institute for Advanced Studies. I just want to start by saying welcome to everybody. It's great to see such a diverse and interesting group of people. I hope that everybody has a fruitful day. And if you need anything, of course, ask either myself or Duygu. I also want to say a big thank you to Duygu for the energy and skill that she's put into running this pretty complicated project. So it's really Duygu's been driving this. So thanks a lot for all your energy and efforts. Unfortunately, we're in the middle of our 5-year review in the geophysics section, so I'm going to have to leave at lunchtime back to be interrogated by the panel. But I hope you enjoy your day. Thanks.
Thank you so much, Chris. Good morning, everyone. Welcome to the big workshop. We are delighted to have you here. So my name is Duygu Kiyan. I'm a geophysicist. I work at the Dublin Institute for Advanced Studies. I am one of the co-PIs of this big project. So this workshop has been organized as part of the big project, which is co-funded by Sustainable Energy Authority of Ireland and Geological Survey Ireland. Before we start, I will give a quick overview of the project, which some of you are familiar with. So DIG is a significant geothermal energy research project that aims to explore the potential for low enthalpy geothermal energy on the island of Ireland. The project officially commenced in 2020. During the course of the research program, we funded 5 researchers. The overarching objective of the project is to create an improved resource map of Ireland, and the key objectives are to determine the regional geothermal gradient in Ireland using geophysical, geochemical and petrological data sets at the regional scale to investigate the thermochemical crustal structure and secondary fracture porosity within the Upper Devonian Munster Basin. And at the local scale, to identify and assess the available low enthalpy geothermal resources at the reservoir scale in the Munster Basin. Our demonstration site is called Mallow Warm Springs area, using joint interpretation of Magnetotelluric's passive seismics modeling results together with structural geology and hydrochemistry program. So why did we focus on Mallow? Mallow on this map, you are seeing these green triangles. These are the warm springs which have temperatures more than 12 degrees. So you can see that they are grouped in the North Leinster and in the North Munster. So the North Leinster ones. These springs were investigated by another geothermal project almost 10 years ago, and for this project we are focusing on the ones in the Mallow region, and they both are located to the south of the Iapetus suture, and the North Munster group occurs to the north of the Weatherill front, suggesting regional tectonic control. And there was a work which was done in 2010, the hydrochemistry of thermal waters in the Mallow Mitchelstown Springs suggests a deeply buried aquifer source in the region. So a major component of the DIG project is the exploitation of the geophysical-petrological inversion code that has been developed by Javier Fullea, who is one of the co-PIs in this project, and he's going to actually give a talk today, and his colleagues. The strength of the code involves integration of vast array of geophysical and petrological data sets. And in Ireland, new geophysical and petrological data sets have been emerging, and we have used these data sets to map lithospheric thickness beneath Ireland and to refine and calibrate the temperature maps of Ireland. Emma Chambers will be talking about this research in session 1 today. As part of the As part of the work package 2, we carried out new thermal conductivity measurements on selected lithologies, limestones, and other undersampled lithologies on the island of Ireland, and these data sets are currently being integrated in the modeling. As part of the local scale research, as I said, we focus on the Mallow Warm Springs area. We carried out Magnetotelluric and passive seismic data acquisition around the warm springs in Mallow to image conduits and pathways supplying the thermal waters to the surface. And we are also developing a 3D structural model for the Mallow region, and we also have a hydrochemistry program which aims to characterize deep reservoir water composition, which will help identify potential convective pathways and mixing zones. And we are going to hear from this research, Pat Meere, Chris Bean, John Weatherill, and myself will be talking about these research results today. And apart from the DIG project presentations, we will also hear from our guest speakers who kindly agreed to give a talk on their exciting works. We also have posters on display. Please visit them during lunch and coffee breaks. The workshop will end at 5 p.m. and will be followed by a networking event with finger food and refreshments. But this is not the end. We booked a space at O'Brien's, which is on Sussex Road. It's just 5 minutes walk from here, so we can go to the pub and continue discussions over there. So I am now going to hand over to Emma Chambers, who couldn't be here today in person because she's unwell, but she's going to join us online. So thank you very much.
Thanks, just check. Has that started displaying? Can you see that properly?
Yes, perfect.
Perfect. So sorry, everybody. I caught COVID, so I really wanted to be with you, but you really don't want me there. So yeah, I will present remotely. And also, I've got a few, if you want more information on the thermal conductivity thing, stuff, all the model therm projects, there's a few posters, as Duygu mentioned, in the other room. And for anyone that scanned QR codes, turns out these have expired. So please just go to the project websites. So without further ado, I will kick off. So today I'd like to present to you new 3D temperature model with uncertainty for Ireland. And the point of doing these new temperature models was to kind of understand the whole subsurface temperature of the whole of the island of Ireland. This has been done before by other projects making temperature maps, but the key improvement here is that we have uncertainties associated with these, and we have tried to ground truth these models. So what do we need to create these models? Well, the first thing is that we need to know where the heat is located beneath the subsurface. So this requires us to know lithosphere, asthenosphere boundaries, because hot, see if I can get a pointer on here. Hot asthenosphere, when it's closer to the surface, due to thinner lithosphere, will have warmer temperatures with thinner crust. And we also have heat from radiogenic heat sources in sediments in the crystalline basement. So these will also provide sources of heat. So we need to work out where these are. Excuse me. So what information do we need to make a 3D subsurface temperature map? Well, for this, we require continuous layers for the input parameters. We need to know some of our boundaries, so such as the elevation, our topography. We also need to know our moho depth to a degree and layers within the crust that we can then also invert for. What we also need to know, though, is the surface heat flow, as well as our thermal property information, such as radiogenic heat production and thermal conductivity. And so we have created, as part of DIG, a new thermal conductivity map, which we will also be updating again with the new thermal conductivities that we've recently been making, thanks to GFZ, UCD, and GeoServe, and a range of collaborators. So thank you. So one of the key parameters that we added was seismic data, and this was crucial key component adding into these temperature models because it constrains our lithospheric boundaries. And as I said, the lithospheric thickness is a control on the geothermal gradient. So if we've got thinner lithosphere, we have warmer geotherms because it's close to the surface. And if we have thicker lithosphere, we get cooler geotherms. Now, this was an excellent time to do this project because we are using surface waves to constrain these boundaries. On this map here, you can see stations across Ireland and Britain, and we extract the surface waves between pairs of stations, cross-correlating them. And you can see that we have many pairs of stations, which is fantastic. We managed to extract Rayleigh waves, dispersion curves, which is from Raffaele Bonadio, and then we also extracted love wave dispersion curves. And these could then be turned into maps across Ireland and Britain. And you can see that there are some variations between the love and the Rayleigh waves due to anisotropy, but there are changes across Ireland as well, with lower velocities and higher velocities. So we take all this information and we put it into a joint geophysical-petrological inversion, which is the WinterC code developed by Javier Fullea, and he's going to talk about this more in a later talk. And you can see that we take all of these input data sets that I have described above, we put it into this joint geophysical-petrological inversion that relates these parameters, and then directly inverts for temperature. So this is our key output parameter that we're most interested in, is the temperature of geothermal gradients. But we also get outputs such as lithospheric thickness, shear velocity, anisotropy, and some metal composition, heat production, and density. And I should add that the version of the code that we're using requires a 3-layer crust, so just upper, mid, and lower crust. Some of the input parameters are averaged for the whole crust. Some of those are assigned to individual layers. So we do this, and what we do is that this is done in a 1D sense. So we do this on 1D columns. As you can see here, each of these black squares is a 1D column, 20 by 20 kilometers laterally. And when we do these inversions, we fit the Rayleigh and love wave dispersion curves, we get a misfit, and we also fit the heat flow elevation and invert the heat production. But we also get out temperature, velocity, and things. So if we zoom in on the temperature and the velocity, we can see some trends start to appear. Now, each of these coloured lines relates to the same colour as the square in the diagram on the left. And you can see that in areas where we have thicker lithosphere, so the green lines and the blue lines on here, we see that we have cooler geothermal gradients, as we would expect. In areas where we have thinner lithosphere, so the red and the black lines, excuse me, we have warmer geothermal gradients. But what was very interesting to know is the red line is significantly elevated beyond the rest of the lines. And this is because it's actually located on top of the Duygu granite. And as we mentioned before, we have two main sources of heat. We need to know our lithospheric boundary, but we also need to know radiogenic heat production. And it turns out, as this is a granitic area, it's got high radiogenic heat production. So this is boosting our geotherm even higher. Great. We could do this at every single point across Ireland. These have been done on a 20 by 20 kilometer resolution, and you can then interpolated to create these. And these slices are at 2, 5, 10, and 30 kilometers depth. The whole model does go down to 120, but we mainly care really about the upper 5 kilometers because that's where we might be extracting geothermal heat. And you can see some trends in the areas where we have granite, so such as the blue highlighted blue areas. You can see that we have warmer geotherms on the whole, warmer temperatures. Beneath the red zone in here, we have warmer temperatures, which is the Antrim lava sequences. Whereas in the Irish Midlands, we have cooler temperatures and kind of a general cooler trend from in the southwest and then warming towards the northeast. But what was also important about this was doing some uncertainty analysis. And so we tried to think about how we were going to do this, as there's uncertainty in quite a lot of our input parameters. So initially we thought about our main ones that control temperature, such as such as LOB depth, boho depth, the radiogenic heat production, and thermal conductivity. While it's an input parameter, it's not inverted for. So we also included this as one of our parameters. We initially thought, as our inversion tries to fit all these parameters, what happens if we keep these parameters fixed and change these individually? And this is how will our temperature change? So we kept all of those parameters fixed, and this is what the lines show. The black line is our best temperature model, as shown on the left, whereas the blue lines are if we keep all parameters fixed, with the thick blue line the mean, and the dashed lines the min and max, and the band of blue is the one standard deviation. However, in our inversion and in real life, our parameters trade off with one another. It's not as if we would ever keep all parameters fixed. If I change the radiogenic heat production, I expect my surface heat flow to also change to compensate for that. I wouldn't have a rock that I could only change one parameter and nothing else would change. So it seemed more realistic for us to only fix one parameter and then allow all the others still to change with one another, as you would normally do in the inversion. And that's what the green lines show. Again, the thick green line is the mean and the one standard deviation. And these will relate to here. Sorry, I should have zoomed in. So this is from 0 to 5 kilometers depth and shows exactly the same thing. And this is where they are located. So you can see that on the whole, if we look at just the green lines, which is fixing one parameter, which seems more realistic, you can see that our trends are certainly at 2 kilometers depth. They're only changing by about 3 to 5 degrees Celsius at 2 kilometers depth. Which is good that we don't have that much variation. And seeing as this seemed to work for fixing one parameter, we decided to do this at every single point and see how that changed. So this is what this looks like for each of the different depths. Now, I've shown it from 2 to 30 kilometers for each of these, just to show that it does gradually increase with depth, as we would expect. But what's more useful probably is this slice at 2 kilometers depth. And you can see at 2 kilometers depth, which is one of our kind of target depths due to the temperatures, we have an uncertainty of between about 1 degree to 5 degrees, with 5 degrees the maximum only being in a few areas, and kind of the average is about 3 to 3.5 degrees Celsius. It should also be noted that we did remove models that seemed un-Earth-like, and so this was deemed as taking any models that was more than, from our best temperature model, we calculated the misfit of the entire inversion. It's an output parameter from the inversion, and anything that was 5% away from our initial inversion, we deemed that to be unearth-like and removed those. It allowed us to keep in enough models so that we could calculate a root mean square uncertainty, which seems the best way of displaying the uncertainty for this type of work, while removing unrealistic models. And you can see that if we do those from those range in models, these are our minimum temperatures, our maximum temperatures at 2 kilometers depth for each column, and mean temperature. And the mean temperature is pretty similar to the original best temperature model, using the best parameters that we had. So that's good. We also obtained the geothermal gradient shown in the top left here, which ranges from about 19 to 38 degrees C per kilometre, from 0 to 2 kilometres depth. And we also get 30, 60 and 90 degree isotherms from this, which is quite useful in the geothermal industry. These are kind of key depths to these boundaries. Another output is radiogenic heat production. This is taken, as I said, we use a 3-layer crustal inversion, but for radiogenic heat production, this is one parameter for the full crust at the minute, which is very much an average and an approximation, and will be refined in future versions, but at the minute, this is what it is. And the average for the full crust ranges from about 0.5 to 2 mu watts per meter cubed, which is similar to previous studies. Another key component is new MOHO and LAB depth maps for Ireland. These range from 25 to 33 kilometres, and an LAB depth ranges from 78 to 118 kilometres, with thicker MOHO and LAB depths in kind of the central Ireland and in the south, and thinner beneath the Antrim basalt. So quickly through to some quick interpretations of those maps, because there's a lot in there, so I can only do a little bit of interpretation. But one interesting area that we found was this basalt region. So that's the bit highlighted in red here, and also this dark region in here. We found that we had elevated temperatures compared to the background, but what was also interesting is that they also had very low surface heat flow from a previous study. Now, basalts themselves have low thermal conductivity, so what we think is potentially happening beneath the basalts is that the basalt layer is acting as a thermal blanket. So heat is rising beneath this region, but it's getting trapped beneath this basalt area. So it could be potentially a great area for geothermal exploration. And I think the Gemini projects and other projects are now starting to kick off and exploiting this, which is great to see. Another interesting area was the granitic areas, which are these blue polygons shown on this map here. They have high temperatures, but they're also quite variable in their temperatures and also had very variable surface heat flow, with some regions being quite high, such as in Duygu, but in Leinster, these were quite low, and other regions. So this radiogenic heat production was quite variable. So, and the radiogenic heat production here is also variable even. So what we think is happening is that the granites have different compositions and are potentially different sizes and located at different depths. And this seems to match well with previous geochemistry studies, which suggest definite compositional changes between the Leinster granites in particular and some of the Galway granites and the Donegal granites. Now it's great, but as I mentioned before, there have been other temperature models in Ireland. So what makes our temperature model, how do we know our temperature model is any good? So there haven't been many direct temperature measurements in Ireland that have gone very deep. This is starting to improve with more recent projects. But we took what deep temperature measurements that we had at the time. And thank you to people that have provided these, GSI, GeoEnergy NI, etc. And we basically took the borehole direct temperature model measurements, which is this solid black line, and then mapped our coloured line as our model. I've also plotted on in the grey lines the two previous temperature models that they had to see how they fitted. And as you can see, in some locations, which are highlighted by these triangles on here, we get a very good fit. And in Ballinlea and Portmore, these are actually in the same grid cell. And because we don't change the thermal properties that we input between them, there was no way we could ever fit both of them. So in the future, we would make it so that our grid cells for thermal property data are variable so that you could then match these variations, as well as having a multi-layer crust. So to conclude, we produced new subsurface temperature maps of Ireland with uncertainty. Areas of thinner lithosphere have warmer geotherms, as we expected, and at crustal depth, it seems that the thermal property data is the main temperature control. So those granites with radiogenic heat production, those are the radiogenic heat production is more prominent. So areas with granites have our warmest temperatures, and the basalt seems to be acting as an insulating layer, elevated subsurface crustal temperatures. We've created additional new models for all of these different parameters and more that I don't have time to show. So I just want to say thank you for listening. Thank you to our funders. For more information, please see diggeothermal.ie and email me if you have any questions or want further discussions on anything. So thank you.
Thank you very much. We have 2 minutes for questions before the next speaker starts. Do you have any questions, or you can keep them for the discussion as well at the end, of course. Sure, Ilmo.
Thank you. Emma can hear us.
Yeah, I can hear you. Yeah.
Thank you for a very thorough presentation. That was very interesting to hear. Just a comment on your temperature maps. You're calculating then they with 20 kilometer times 20 kilometer resolution. They are one-dimensional models.
Yep.
Then in a 3D presentation, you show the variations of temperature. But if that would be truly a 3D thermal conduction model, you would probably have less temperature variations at 2 kilometers or any depth level. All right?
Well, so we did it at the 20 kilometer resolution because that's the resolution of the seismic data, so that will hopefully improve. But by doing it as a 1D analysis, we don't take into account the lateral heat production. So in the case of the granitic areas, these will probably expand a bit at 2 kilometers because their heat will radiate outwards. So it might get smoother in the sense of those with the temperatures, yes. But yeah, we do need to take into account lateral variations in the future.
Thank you. Thanks, Emma, very much. So we can move to our next speaker, Sergei Lebedev, from University of Cambridge, and also he was with us with the Norden Institute for Advanced Studies.
Thank you, Duygu. I would like to show you some of the work we've been doing with Javier Fullea and Aoife and Rafael Bonadio. We have started this when we all were at DIAS, so it's nice to come back and show it here. If I may start from the very beginning, the Earth is cooling as we speak. A lot of heat is transferred from the hot core to the cold surface. And this is the heat that most of geothermal energy resources come from. In most of the mantle, this transfer of heat is via efficient, fast conduction, but in the thermal boundary layer at the top, it is by slow, inefficient, conductive cooling. And of course, this thermal boundary layer is the lithosphere that makes the tectonic plates. The lithosphere varies laterally in its thickness and temperature, and this has a big effect on geothermal resources, as well as on volcanism, composition of magmas, mineral resources, seismicity, seismic hazard. Thicker lithosphere has lower temperature everywhere. It lets through less heat, so that the heat flow at the surface is lower. It also is mechanically stronger, and thanks to the lower temperature, it has higher seismic velocity. So we can use seismic data to map the lithospheric thickness variations. We can, in fact, use seismic tomography to derive the tectonic regionalization that is surprisingly accurate. It captures, for example, if you look at cratons, captures boundaries of cratons where we know where they are at the surface, but it also does so where the boundaries of the surface are covered by sediments or ice. As Emma has explained very well already, the temperature near the surface, which we care about for geothermal energy resource exploration, depends on the thickness of the lithosphere and also on the crustal heat production and thermal conductivity in the crust. So these few profiles illustrate variations in heat flow and temperature thanks to some large, perhaps exotic variations in heat production, as well as in lithospheric thickness. The even relatively slight variations in the lithospheric thickness produce a few tens of degrees difference in the crust. So can we just take seismic data, make tomographic models, and convert it to temperature? Unfortunately, that doesn't quite work because of the non-uniqueness of geophysical models. In the broad period range lithospheric scale, we can distinguish clearly thick and thin lithospheres, but if we look at fine scale variations within the lithosphere, they become highly uncertain. So these are actual uncertainties of the profile computed for this knot spacing in the model. Try to pick thickness of the lithosphere to within 20 kilometers. That's very difficult. So the solution to this that we propose is what we call seismic thermography. We recognize that inferring temperature from non-unique tomographic models doesn't work. It gives implausible oscillatory geotherms. And what can solve this problem is thermodynamic inversion of seismic data directly for temperature. This is largely composition insensitive, and that's why we can focus on this relationship. And the critical point of this is accurate, complete extraction of information from noisy data, as I'll show you a couple of illustrations for in a minute. So seismic thermography or infrared thermography is a term that's been already in use in medicine and remote sensing for temperature measurement, material characterization, and the concept translates naturally to temperature within the Earth, measuring temperature within the Earth using seismic thermography. The core of this is thermodynamic inversion of seismic data directly for temperature. We build on technique of seismic tomography, computational metrology, and thermodynamic inversion. We use the methods of multi-observable inversion that have been developed by Javier Fullea and collaborators over many years. But here we focus specifically on temperature. And we can do that because the temperature-seismic velocity relationship is not sensitive to composition. And out of this, we get more accurate thermal models and even seismic velocity models than tomography to begin with. Our inversion parameters, so if you implement this general approach to the lithosphere imaging, our inversion parameter, main one, is the lithosphere-asthenosphere boundary depth, from which we can compute conductive geotherm or add transient effects. We can also vary the temperature in the asthenosphere and some other parameters. And from the temperature and composition and depth, we can compute elastic properties and obtain synthetic observables, which you can compare with data and set up an inverse problem. Out of this, we get also predictions for heat flow, elevation, and other observables. For example, if we take the average Phanerozoic lithosphere, like in Britain, Ireland, Western Europe, and other relatively young places, we can get a very accurate profile with about 80 kilometer thick lithosphere. And we can fit the data within well below 0.1%. So this model explains data very well. And this ability to pinpoint the lithospheric thickness at this new level of accuracy gives us power to solve many problems that could not be solved before. For example, one old puzzle is the strangely uneven distribution of seismicity in Britain and Ireland. We know that the two islands were formed in the same Caledonian orogeny with the northeast-southwest tectonic boundaries in both islands and major faults also going northeast-southwest across them. And yet seismicity forms an entirely different shape, which makes it a very old puzzle. Now, if we look at the lithospheric thickness determined at different parts of the island, in Central Ireland we see 110 kilometer thick lithosphere, whereas in Western Britain it's something like 85, 90 kilometers. And if we compare now the distributions of proxies for lithospheric thickness with seismicity, now this shows a very good match. And we can determine quantitatively the thickness of the lithosphere and see that it's variations of about 15, 20 kilometers that appear to cause this localization of seismicity in this band, north-south band in the west of Britain. Almost a large majority of Irish earthquakes are in the very north in County Donegal, and this is also where the lithosphere is thin. So this caused some interest in international press and in the Irish presses. Some of you may have seen the tabloids focused not on the lack of earthquakes in most of Ireland, but in the magnitude 2s in Donegal. And of course, back to geothermal exploration, this is what we have been applying in Ireland, and Emma showed her great work on mapping the resources across Ireland. We can also take this approach to a larger scale. We can do it at regional scale, continent scale, and move towards the global scale, as we have been doing also in the project Inner Space, led by Helen Doran, who is here in the audience. But how do we do that, and how do we make sure our models are accurate? And what is the challenge here? Well, random errors in phase velocity curves, which is our seismic data, do not matter very much. So here's a large random error, and it all cancels out. We get pretty much the same model with different implementations of noise. But correlated errors, those that extend over broad period ranges in our data, can have a large effect. For example, 0.5% correlated error means, as most would say, 0.5%. It can cause in the worst case scenario, a huge effect makes spheric thickness estimate basically meaningless. It can vary from 100 to 250 nodes for the same data. And even very small correlated error by 0.05%. So here there are the different models in the data. You can't see it. It's all well below line thickness. They can still give you noticeable differences in spheric thickness. So the challenge here is to have well-tuned inversions. A misfit like this could result from poorly tuned inversion, where we don't converge all the regularize poorly, and also to get the most accurate data with no systematic biases. So in step 1, we obtain such accurate data, and in step 2, we relate the data to temperature and find models that explain the data while minimizing the impact of errors and extracting the information as completely as possible. So within the wind project InnerSpace, we have been, as an example, working on North America. So how do we do that? How do we get the best possible data? In the US, thanks to the recent dense deployments of seismic stations, there are very dense networks and high-frequency measurements. For longer periods, and outside the US and Canada and Mexico, these datasets are not available, so we have to use other models. So how do we best merge different datasets? We aim to get a very broad period range of the measurements, sensitive from the crust to the deep upper mantle. We find the state-of-the-art datasets and find the optimal way to combine them by using weighted averages everywhere. So in this case, the array measurements from Ekstrom and Schmann et al. For short period ambient noise measurements, and we have our own waveform tomography for longer period measurements. We can compare the do some statistics on systematic differences between datasets and look at the errors, where the errors become large. And we should focus on one dataset rather than the other. For example, the ambient noise datasets, which give very high resolution at short period, at long period, they become basically similar to long period datasets, but dominated by noise at short wavelengths. So here we have to gradually give more weight to smoother and robust models. And that gives us a set of Love and Rayleigh phase velocity maps, which captures the seismic data sensitivity to temperature and thickness of the lithosphere in very broad period range, from crustal sensing periods to lithosphere sensing periods. Obviously, the dominant feature is the Canadian Shield, which is with its counterpart Western US, where a lot of tectonics and volcanic processes happen, and we can obtain these phase velocity maps in a very broad period range, up to 300, 400 seconds. So to summarize, the lithosphere scale thermal modeling enables us to map geothermal energy resource potential at regional scales and continental scales. We will know the temperature when we drill, obviously, but to map at regional scale, it's very useful to combine available data with that come from direct measurements with geophysical models. Lithospheric geotherms are best constrained by seismic surface wave data, and the best way to extract this information from the data is by thermodynamic inversion, always for temperature. We are seeing increasing successful applications in different scales, and apart from geothermal applications, we also find very interesting new patterns in how the lithosphere controls intraclate volcanism, mineral deposit generation, and seismicity and seismic hazard. Thank you very much.
Okay, good morning to everyone. I'm part of DIG as well, and I've been actively involved in Emma's work. But what I'm going to be presenting you here is South Africa. But it's the same methodology. It's the same sort of integrated geophysical-petrological inversion. And this is work that is being done for Project Inner Space that was introduced earlier on today, and Helen is one of the big names there. So basically, we started working in Africa. Africa, you can see on the left plot, that's a distribution of heat flow measurements from a recently reviewed and assessed database from GFZ. And you can see that there are only a few measurements. Some areas are largely uncovered. So people, what they do is they, using different techniques, statistical techniques or neural networks, things like that, they try to combine the few existing measurements on heat flow with other geophysical data, like, for instance, tomography or gravity, surface topography, and so on. And these are some predicted surface heat flow maps in Africa. This neural network, and this is some similarity analysis. You can see that, yes, there are some common trends, but in many places there are differences. And that's when we try to come up with some different kind of modeling. So what I do is to try and bring a physically informed inversion. This is what has been already introduced by Emma and Sergei. So essentially, if we want to know the temperature distribution, there are some ingredients that we must know, have in the table. One is the thermal thickness of the lithosphere. This is crucial, and this is going to be constrained by surface wave tomography data, as Sergei mentioned. There's the radiogenic heat production in the crust as well. There's the thermal conductivity, especially of the topmost layer, upper crust or sediments. There's the crustal thickness, how much crust radiogenically active you've got. And there are also transient effects that are of relevance in regions of thin lithosphere, recently active lithosphere. So the first ingredient for us is surface wave tomography, and because this is the best kind of data to resolve the lithospheric structure, the thermal thickness of the lithosphere. And in here we're using surface wave tomography data, actually from Sergei's group, in the form of dispersion curves for Rayleigh and log waves in single locations, because this can be to a large extent modeled in 1D. So it makes sense to model the 1D geothermal in several locations. And this is precisely the method that it's been applied in DIG for Ireland. This is from Emma's recent work. And what we're seeing is that we first need to capture the contribution from the lithosphere, but then if you have borehole data, for instance, you need to refine the geothermal by looking at things like, what's local heat production and the thermal conductivity. Once you tune those things, then you have a very nice fit to the borehole data. So the method is working well on that. And that's the distribution of 1D columns that we inverted in Africa. We're using Rayleigh waves from this work by Sergei's group as well. And for LOF, we're using also tomographic data from an earlier work. We are incorporating a newly compiled sedimentary thickness map in Africa from interpolation of control source, seismic, and borehole data. This one here from a group in Cambridge. And we also include as input as the average surface temperature from this work Lembridge. That's the input surface heat flow map interpolated. So you can see that the coverage is very poor in many regions. And we can compute actually statistically the dispersion from these measurements, which you can see on the right plot. In the areas where you see the yellow color, that's basically we assume 20 milliwatts per square meter where we don't have anything. And the rest depends on the dispersion of the data itself. So it's in some areas it's more or less okay, small, relatively small, but in some areas it's actually quite, even though there are lots of measurements. For instance, here in Algeria, the dispersion is not small. And this I forgot to mention, this is from the recently reviewed database from GFZ for surface heat flow and also for thermal conductivity. in boreholes, and this is also something that we use. And you can see here the average computed based on the distance to each of the points. And this is, again, the dispersion. And again, this color here is for points where we don't have anything. This is something that goes into inversion as well, at least for the topmost layer. Thermal conductivity is a crucial parameter on this whole thing. So in Africa, if you look at the distribution of the upper crust and the sediments, the thermal conductivity, if you take an histogram of the most data that are labeled and coincide with the sedimentary grid and all, you get a distribution that has a median or average value around 2.5 to 2.6 watts per meter per Kelvin. So that's a good estimate for the topmost layer. In fact, if you plot the conductivity versus depth for the boreholes, this is the dashed lines here. You can see that they fit very nicely the classical Chapman-Furlong expression with these parameters for the upper crust. The temperature variation is actually decreasing the thermal conductivity quite significantly. And then for the mid and lower crust, we use this other set of parameters. In this case, the pressure term compensates the temperature variation, and then it's kind of flat. So yeah, and well, this is the expression basically that we use for the topmost, for the room condition thermal conductivity of the sediments and upper crust. So basically, the inversion is said in a way that the radiogenic heat production of the sediments and the upper crust, we invert for it, and this is going to be largely controlled by the input surface heat flow, depending on the uncertainty. For the middle and lower crust, in the case of Africa, because data we have are not very sensitive to the crust, we use constant values of 0.6 and 0.4 microwatts per cubic meter, respectively. We use the temperature and pressure dependent thermal conductivity, and we use for the room condition thermal conductivity value at the surface, wherever this is available, the data from the GFZ database with this expression, and we use also the sedimentary thickness compilation from Seismic and borehole data. That's the result of the inversion. On the left, you can see the lithospheric thickness map, and you can see that we clearly see the cratons as thick regions. And then we have relatively thin lithosphere in the African rift and northwestern Africa as well. So there are these more or less three regions that we will see, and the central part of Africa, which is kind of in between. On the right, you can see the crustal thickness, which is also based on prior information. We are using crust 2.0 and let it vary within statistical uncertainties, statistically determined uncertainties. This is a part, as I mentioned, of the project inner space, and in fact, these layers, not maybe this one, but the earlier models, are introduced into this geothermal exploration opportunity map, beta map, which I invite you to check in this link here. It not only contains these models, it contains a lot more data, including crustal phases, falls, energy demand, lots of things. So it's very interesting. I recommend it to you. So this is our predicted surface heat flow model in Africa. And on the right, you can see the measurements, which this is what we have at the beginning. In this case, we are assuming the uncertainty coming from the dispersion in the surface heat flow data. So you can see that, as we would expect, the cratons are in the 40 to 50 milliwatts per square meter, more or less. Then we have the central part, which is around 60 something. And then clearly in all these regions in the East African Rift and North Morocco, you can see that's quite thin, not thin, well, thin as well, but basically high surface heat flow. Actually in here, the transient effects kick in and produce a significant increase in the predicted heat flow as well. But this map, we can do different things with the input uncertainty. For instance, if you compare these two maps, you can see that some of the features, for instance, here in Algeria, are not present here. And this is because the uncertainty in the input heat flow is large there. But we may want to force the inversion to capture these local features. And we can do that by reducing the uncertainty artificially. And if you do that, then you get a predicted surface heat flow map like this one here, where you now can see that main trends are still there. But essentially, for instance, here we lost the high heat flow values because there are no measurements. But on the other hand, for instance, this high value here is present. So we're still trying to figure out how to weigh the different data sets, but at least we understand the effect of putting more weight on one or the other data set. And we can also predict temperature gradient, which you can see here on the left. And again, it's the same. Gradients are around 20 or something Kelvin per kilometer, central part, and then high heat flow values in excess of 40 Kelvin per kilometer in the East African Rift and North Morocco. And temperatures predicted at 2 kilometers. Again, the same. Here you see more structure as well because there's a lateral thermal conductivity variation that is producing some smaller scale features here. Yeah, that's how it looks like. So to summarize, we have applied this integrated methodology where we basically the core of it is that we try to link the rock properties by means of temperature and pressure and composition, as Sergei explained. And in doing that, we have come up with a new thermal map for Africa, including prediction of surface heat flow, alternative models, temperature at different depths, and also interpolated connectivity data. So the next steps for us would be to try, and particularly in regions with no or very few data points in terms of heat flow, to try and interpolate that laterally in a meaningful way. And then, we're doing that for all continents, essentially. So that's it. Thank you for your attention.
Next speaker is Aoife Braiden from Geological Survey Ireland, and she's going to talk about how these exciting geothermal research projects inform policy in Ireland.
Duygu asked me just to maybe give a little context of where all this research ends up, and on our side, and where we are in Ireland in terms of policy and legislation and the work that the survey is doing. So this is a talk that I gave for something else, and I put in some examples, but actually I think some of the work that you've seen this morning so far, actually, it goes beyond that again, and as you saw, some of it is still either in press or being published, so it hasn't quite made it as far as us yet, but that's the intention. So just to start, to take it back a little bit from where we started about 10 years ago now. So when people talk about geothermal energy in Ireland, that doesn't really mean a whole lot. We don't have what Iceland has in terms of volcanoes and nice big systems that they can tap into. We didn't have maps and all the maps that you saw this morning. We don't have large drill rigs. We don't have the economic modelling to show that this is going to work here. We don't have a lot of onshore deep seismic data. We didn't have any policy or regulation or anything like that. We don't have investment funds or guarantee funds. We don't have a private sector and a big, a sector that was ready to go to do this for onshore development. We don't use heat networks, generally speaking, small networks maybe, but not district heating like they do in Europe. And we didn't have public information about this, awareness, or political awareness that this was a possibility. So we thought this is obviously a great idea to start working on this, having none of these in the background. And then when you look at internationally where we are and the amount of, particularly say if we're focusing on heat here rather than for electricity. So if we're looking at heating and cooling and district heating and cooling plants. So these are the numbers, these are the latest numbers from the European Geothermal Energy Council, and this is 2023 figures. So these numbers are globally, but there's 261 district heating systems in operation for geothermal in EU member states, and none of them are here. So we're a little bit behind the curve. You can't see that very well, but that actually says that 94% of Ireland is suitable for shallow geothermal heating systems. But because of a lack of awareness of policy, data, public awareness, demand for it. So these are some of the barriers. And what are we doing with these? And we don't have information around the uncertainty either for the geologicals. As you saw, it's getting better. So I'm just going to don't worry about the detail at the bottom. I'm going to come back to some of these individually. But this is just really to give an idea of where the research ends up. So the reason I have an asterisk there is when I'm talking about this, I'll leave to Rory and GSI colleagues later on to talk a little bit about the GSI research and work that's going on. I'm talking specifically about the research that we fund, so the kind of projects that you saw this morning, and how that fits in terms of supporting policy, but also the wider geothermal sector in Ireland. So the data that the Geological Survey makes available is available to anybody. We don't just feed into policy, we make stuff available online for free, and that means that any SME or sectors or businesses can use all that data. So the kind of maps and the data products that we produce are to support the sector overall. So if we go back to 2015 and Tally and colleagues from the Groundwater, which is now the Groundwater and Geothermal Unit, had produced a ground source heat guide for homeowners. So this is your kind of small residential scale work, and they had been doing some work trying to get a bit of traction in the geothermal energy side and where we go with it and what it needs to look like and what we need to do. And then from there, into 2016, the survey published a research roadmap, and that helped in terms of boxing off some funding for geothermal, well, not geothermal specifically, but for research projects that could then support various different activities that the survey were doing and policy and other sectors in Ireland in geoscience space. So these are the kind of starting points from 15, 16. And then our director met some colleagues at a meeting in Europe, and we ended up joining the Geothermic network. So this is a network of research funders across Europe who get together to support transnational projects, which is all about knowledge sharing and trying to get capacity in Europe in different spaces. In this case, Geothermic one is for geothermal energy specifically. So we joined that, which that in itself was an interesting. My first meeting was, because I did it alphabetically, I was after Iceland. We had to talk through about all the projects that we had happening nationally, which was, my talk was very brief, put it that way. We had a couple of shadow projects happening at the time only. But interestingly, the big problem that the Icelandic guys were having was, how do you image below basalts? And they couldn't figure it out. So they drill a hole. The last 5 years, they go, okay, that's done. Move to the next one. Drill again. And they were having real problems. And it turns out that was something that some of the researchers in Ireland and Chris and the guys could feed into in terms of basalt imaging, because we had been funding it for other reasons. But anyway, some of these, so we funded a couple of international projects. So GeoUrban, that GDG in Ireland were involved in, and Co-Seismic, that Chris and the guys were involved in. And these just allowed kind of capacity building in Ireland, really. And then in 2018, we had our first workshop on deep geothermal in Ireland. And this was something that myself and Sarah put together, Sarah Blake. And we had about 50 people in the room with Beggars Bush, and we were really starting from scratch. We got people in a room, we said, okay, what is it we need to do? What does it need to look like? And we pulled in some of our European colleagues that we'd met through the Geothermal network. And then, as you saw, the GoTherm project, which was one of the first ones that Javier had and Ben, who worked on the early maps, was funded through a joint project with the Irish Research Council. And that was one of the smaller projects that we've ever funded, and the amount of work that has come from that has been pretty impressive, I have to say. And that was looking at gathering up what data we had already and what could the guys do with it. The original map that we kept seeing everywhere, myself and Sarah would go to things in Europe and here, and we'd see this map that had been produced in 2004, which basically said that 2.5 kilometres, whichever slice that is, that it was about 20 degrees in Cork. And it was more to do with just a lack of data. So it was because, as you can see, the boreholes that are on that map are all from the Midlands up. And so there was just a gap. But this map kept reoccurring in other meetings, and it was taken into EJEC presentations and things like that. And we're going, please stop using this map because it looks like it's cold here and it's not. So that was the idea in the GoTherm project, was to try and improve this. And where do we go next? And you've seen this morning how advanced we've come since then. So from that specific project, before the things you saw this morning. So this is the work that Ben and Javier did and published in 2019. The map, the top map there is what was produced instead, and that was just an image that we used. We actually used it for the cover of the document later on, but the research that was published from that could at least say it's okay to stop using the 2004 map, because when we asked people to stop using that map, they said, okay, well, give us a new one. You know, they don't like just taking something away; they want to replace it with something better. So, and then the survey, the idea was to produce some slices like this. As you can see, that's all moved on significantly since then. So then we funded and co-funded with the Sustainable Energy Authority of Ireland. So we kind of shoved geothermal energy into their funding scheme as well. They weren't funding any geothermal energy projects before then, well, they were, but not at scale and not in any kind of structured way. So this was a mixture of shallow and deep projects, with the dig then, which has been extended a little bit, which is why it's still carried on. Funded through that scheme, and you can see the kind of work that has generated. So the idea then was to take the maps that have been produced in earlier projects, add whatever's coming from DIG and now Emma's project and various other things, and to see where we can get beyond that to inform policy, legislation, helping build the sector, all of those things. In parallel to all of that, the Geological Survey was also doing some work. And I'll leave it to Rory to match some of these, or Tally's was involved in them. She's in the room here as well. And these were projects that we were involved in as a survey with other international surveys and across Europe. So as part of GeoEnergy, again, one of these kind of collaborative networks. And there was 2 different projects, so Muse and Hotline, looking at slightly different areas. But it was a chance to build some capacity internally in GSI as well. And then again, on the kind of networking side and knowledge sharing side, so we were invited into a coordination and support action called Geothermal DHC, so district heating and cooling. That's just finished last year. And that was extremely useful because that project was more around networking and workshops, and shared a lot of information around policy and legislation and funding schemes and what do these need to look like and how do you get guarantee schemes up and running in your country. And had lots of people that were at lots of different stages. So you had some countries like France who were very far advanced in terms of heating and cooling networks. And then you had us that were kind of starting from scratch, but we had an idea of what we wanted to do. So just being involved in some of these networks is extremely useful. And we then, when we started working with the policy people in our department, I should say, for those who don't know, so the survey is an office, a division within the Department for the Environment, Climate and Communications. So we're embedded in the government department. And when they started working on the policy, we were able to pull in our contacts from Europe to say, these are the people you need to talk to. And these are the people that have similar geology or, suitable rules. These ones, maybe not so much. So then myself and Sarah and a couple of others worked on this, what we just called an assessment for district heating. So when we were talking to people and trying to get some movement on the policy side, the answer we got was, well, what is this? What are you talking about? Who wants it? How is it useful? What are the numbers? Why should we care? Nobody's coming on our door looking for this policy and looking for the legislation. So we have other things to do. And we said, no, this is really important. So we kind of hassled them into it and developed the document on the left. And in that we had a chapter that said, these are the other things that need to be done next. And our department said, well, some of that is not for you because you're the survey, which is true. We'll take that. They developed, at the same time, these 2 documents published at the same time, they developed a framework on what happens next and what needs to happen next in terms of the policy and the legislation that needs to follow and where does all this go next. So they were published in late 2020. And that was a roadmap for policy and regulatory framework of these documents. So then back to the researchy bits. So these are all happening in parallel. But on the research side, then we were doing some work with the UCD group and ICRAG and funded a senior policy advisor there for a couple of years. And so she was helping with looking at some of the kind of barriers to uptake and some of that work that was going to feed into this to try and deliver this framework and what it needed to look like. And then in the meantime, the Geothermal network, which was very successful and has some really interesting projects in there, was absorbed into what's now the the Clean Energy Transition Partnership. There's a little bit of overlap between those. So there's a couple of more projects funded. So the DEEP project that, again, Chris and guys had delivered. And then Result, which was, again, a company-based project with a couple of universities as well, so UCD and DICE involved in that. And as you can see, I mean, the investment that GSI made is not that big in these cases, but it gives access to very big, very productive projects, for want of another word. So, for example, access to information at a drill site where they might be putting millions into an actual drilling project. And then the most recent version of these is under the Clean Energy Transition Partnership, which is Galleries to Calories. So John, working on that. And Legding HD, which is a project down in Cork, which is to do with trying to get heat out of subsurface engineering structures, tunnels and things like that. Then following on from the first meeting that we had, the workshop that we had in Beggars Bush back in our own building, we then had the first annual, we got very ambitious and called it the first annual Geothermal Summit in 2022. And that was trying to get everybody in the room that we thought should be interested in this. And we were trying to push other people who needed to do other work as a geological survey. We should be looking after the subsurface bit. And we were trying to get people engaged and saying, okay, you take the economics, you guys take the policy piece, you guys take the legal piece and things that needed to be done. So that was a very mixed room, but went well and people responded very well to it. So we did another one then. Last year we turned it into a week, which was 3 days, but we called it a week. And that was a mixture of bringing in people from Europe, from the Geothermal Network, and we did a workshop specifically on low and medium temperature systems for cities and campuses and hospitals, things like that. And then we also had a day of field trips and then a day of the full summit. And again, had a very mixed bunch of people in the room, which can be a little bit tricky sometimes to when you're trying to put the scheduling together as to what your audience you're aiming for. In the meantime, the Geoscience Policy Division had been established in the department, and they had a couple of people who were tasked with developing the policy statement. So this came from the work that was identified in the framework that needed to be done. And so, fortunately, they saw the value in talking to us and to researchers and to trying to pull in as much information as possible. That doesn't mean they accept it all. Some of it we gave them and said, no, this is really important. And they said, yeah, but this is a policy statement. That's a technical, geological thing. Thanks, but we're going over here. And that's fine. I mean, that's our job is to inform and advise, and then, it's up to the policy specialists to actually put this together. So last year in 2023, the government published the Geothermal Energy Policy Statement for Circular Economy. Circular economy thing is it's just a kind of an add-on, but the point is we now have a policy for geothermal energy. And with that, they also developed a National Geothermal Advisory Committee, which is going to inform the next steps of that. And that the next job on from that now is to develop the legislation and the regulations that go with that. So it all comes in order. Last year we funded with SFI a research fellow, and this was to try and fill one of those gaps that we had identified, which is the kind of economic modelling piece. Now, unfortunately, that project didn't actually, probably won't finish out at this stage, but it is still a gap that we're looking at, and we're trying to find some other way to fill that. But the idea was to try and help with some of the economics piece, which again is not our job, so it was to pull in some complementary expertise. And then in the meantime, we're also looking at demonstration sites and looking at large heat users and public heat users, which are avoids some problems for us in terms of state aid. And then nationally, I won't say anything much about this because Rory's here is going to talk about it later on, but the National Geothermal Database, so this is internally in GSI. We started to develop the program and the geothermal, the groundwater and geothermal unit, created a separate project around the geothermal database, what that's going to look like, and demonstration projects, and that's evolved quite a bit now, and Rory can give you some data, some information on that this afternoon. But generally, the idea is to create more deep temperature maps and to take in some of the work that we saw this morning and what that needs to look like and how do you deliver that. As a geological survey, our job is to deliver data to the people who need it, whether that's policy or business or anything. the Gemini demonstrator, I'll come back to that in a second, and general stakeholder engagement, and how do you keep up to date with all of that and what people need so that we're funding the right things next. The government policy that came out last year, the next step is the legislation, so the same team are working on that and taking in information from us, and we're feeding some of the research into that, development research. And then various database products. So the Gemini project, some in the room here are involved. This is officially started on the 16th of September. It's a 4-year project, Interreg North-South, €20 million investment. And it is for an all-island set of demonstrators looking at different types of geothermal energy systems at scale. So when I say at scale, it's for, we're looking at a university campus. In Sligo, there's a swimming pool and regional sports centre. And then in Northern Ireland Water and Northern Ireland Housing Executive. And then lots of other bits and pieces that are both on the side of that. So we've lots of exploration work going on. Duygu and the guys are doing some Magnetotelluric work in Northern Ireland. There's some seismic work going on. There's lots of stuff around skills and training and policy and tools for decision makers and lots of bits and pieces. So that's going to be officially launched on the 7th of November. So you'll hear lots more about that in the next few years. So in short, what we were looking at is that if you want to build a new geothermal sector, starting with nothing, you can actually do quite a bit with not a lot when you from a starting point of view. So we have found it very valuable to have and to build research partnerships, both in Ireland and internationally. When I say research, I'm also including the likes of geological surveys in that, and that knowledge sharing. And because so many people across Europe are working at different scales and at different points in the process, different levels of data, you don't need a whole lot of money to get started, although that does increase, and we are now looking for the kind of the bigger scale investments. But hopefully Apple taxes will come in and solve all those problems. It does take time. I mean, it's taken us 10 years to get this far. So in one way, we've made a lot of progress, starting from nothing 10 years ago. And on the other hand, it's 10 years, and you'd hope it was quicker. But I think with the momentum we have now, that'll start to speed up again. There's a lot to be gained from going back and looking at the old data, and I think Javier, you can probably, and yourselves can, attest to that on the project interspace, going back and reusing data that's there and then seeing what the gaps are and looking for more. Some of the conversations that we had with colleagues across Europe, we realised that actually their problem was they had too much money because they just go and collect all this data and then didn't know what to do with it, and they weren't actually getting the most out of it. And then using those international contacts, we've gotten a lot out of that. A key thing is to make all the data and research open access. And it's a policy that Kuhn and the team have brought in the geological survey, and it's really paid off. And we can show the numbers from some of the other programs, and hopefully we'll be able to say the same about geothermal energy. And then hosting these kind of events is extremely useful, because at least it also helps us when we're feeding into policy and the legislation and the teams in the department. It helps us to know where we can get the expert information and help translate that. It doesn't have to be that the researchers all have to be able to speak to policymakers and vice versa. That can be the job of the survey in between, translating all of that and tying those things together and, picking out the bits that are really relevant for them. So, thank you very much.
So there has been a slight change in the program. Pat Meere, who is leading our work on this 5 and the DEEP project, focusing on the structural geology and hydrochemistry, will kick off the session to set the scene for the local scale research. Thank you very much, Pat.
No problem. Thanks, Duygu. Good morning. It's still morning, everybody. Delighted to be here and to talk a little bit about, I suppose, UCC's contribution to the project.
Sorry, Pat, I just need to...
Yeah.
Okay, perfect.
So I'm going to talk a little bit about kind of the structural aspects of the project, particularly in the Mallow area. John Weatherill is going to zoom in at the end of this session and talk about new results. This is very recent work, so it's hot off the press that we're work on the hydro chemistry. Can I just say, first of all, the contributors there, we've got Aisling and Aaron, and particularly Aisling Scully, who pretty much, in terms of all the new stuff that I'm about to present, did all the heavy lifting and is essentially the principal contributor there. Unfortunately, she's not feeling the best, so we wish her well, and I hope I do justice to what she's doing. I just thought as well, since I'm asked to step in here, it would be good just to give a kind of a bit of context in terms of when we talk about faults, and we're back now to, obviously, to South of Ireland and the big project, and in particular, the case study that we're looking at up here in Mallow, up in this neck of the woods. Just have a quick look at the kind of the key structures that we're talking about here, and obviously fault structures. And there are two principal types. These are basinal extensional faults and lake for risk and cross-cutting faults. And I'm going to move over to the west because we've got some fantastic examples, outcrop examples of what we're talking about. It's always nice to put your hand on these structures in the field and get a good look at them. And we're less privileged, I suppose, as we move east to be able to do that. This is the Munster Basin, Upper Devonian Munster Basin. I think the vast majority of people in the room know about this structure. The northern bounding structure, and there's quite a bit of debate on this, but this is one, let's put it this way, this is the Cumnacronia-Killarney-Mallow structure, which I personally believe is one of the principal bounding structures to the basin. We've got a depot centre in the Devonian here of over 6 kilometres, so this was a big, big feature. We've got a second structure, which I'm not going to talk about today, but just for information. The Cork and Meere line, which is, this was a second extensional structure that we see developing at the end of the Devonian into the Carboniferous, and we have ongoing substance to the south of that to produce the South Munster Basin. This is going right back to Ed Williams back in the late 80s, but it's quite a nice simplified view of the geometry of the basin. So imagine this is obviously north-south. This is our big bounding structure, grossly simplified here because you can be sure this was segmented and there was a lot more complexity to it. But it gives us an idea that we've got a depot center here in the west, and the overall bounding structure tips off to the east. Two big fluvial influxes, just to flag that as well. So our depot center here, as I say, is in excess of 6-7 kilometers. We don't actually see the base here, so we're not quite sure just how thick that sequence is. Now, one of the things, and I suppose an important point to make, and the importance of these structures are these early extensional faults. And this is work done by a PhD student of mine, Jürgen Lang, who finished up last year. But he mapped out these in the dark blue here, are these early extensional fault structures. So they're very, very pervasive right throughout the basin. And from the point of view of conduits, they have quite a long and interesting history, all roughly striking, with the exception of further to the southwest, roughly striking east-west. Jürgen did some really nice work, and he demonstrated, again, here are these east-west structures, these basin structures, that a lot of these structures were responsible for siting copper mineralization, early extensional copper mineralization. So we have a history right going back to going into the early Carboniferous of fluids coming up through these fault systems. And quite hot fluids, up to 300 degrees C in some cases. In the field, this is from Allihies. Those of you who know are probably aware of some of the big West Cork deposits. Allihies is probably the largest of those. And this is a nice field example here of some of these early extensional faults. You'll notice in this case here where we've got impacting of this sandstone hanging wall, footwall impact due to later risk and compression. And I'll come to that in a minute. But once you get your eye in, we see these a lot. And again, in this example, and again, it's an eye of faith, I do accept, there are a lot of this vein material along that fault flagging fluid mobility. This is a recent map that Ken Higgs and I have produced for Skelligs, and the reason I'm showing this is that we have one of these early a really, really nice example of one of those early extensional basin faults. This is the Crossbow fault, right down here. And one of the interesting things about that is when you look at it in the field, obviously we see a number of splays off the main fault. This is under this canopy here. And you can see that here at least 3 different splays of the fault. But you see an awful lot of very, very, almost like smearing of fault material. And if we have, if you look, I just go back one actually, we've got a very nice volcanic tuff in this locality. And when we get up and we've got the boatman to bring us right into the cove, you can see here a smearing of that tuff. So this is a kind of classic sin-extensional, not fully lithified kind of behavior. Important to say as well that this structure, this is Kukkonen extending right over to Mallow, which is we're going to talk about in a little bit more detail. We see a lot of volcanic activity. So not only was it conduit responsible for fluid movements, we also have obviously volcanic and igneous activity associated with this structure as well. At the end of the Carboniferous, give or take, we have north-south compression. We have a phase of significant crustal shortening, cleavage development, folding, and reverse faulting. So these early extensional faults, which we're going to be talking about in a second, were reactivated in compression. And again, there is some, examples of copper mineralization associated with that. I suppose the key point to make here is the nature of this structure. This is a cross-section that goes right back to Capel in 1975. It's a lovely cross-section. And you can see there's the bounding structure of the basin, south into the basin. We're on the footwall of the system here. And we're seeing this acted as a significant strain boundary during Bariscan compression. This is Kukkonen, and again, you can see this is Basin-scale. Not an awful lot of net reverse movement on these. Okay, I think it's about 200 or 300 meters in this case. Lovely chevron hanging wall folding, and there's the footwall, relatively flat-lying footwall. So there is a lovely, quite steep dipping is what you'd expect for an extensional structure. A lovely example of what I'm talking about. And Chloe Parker, a good few years back, did a very, I'm not going to go into all the detail here, but did a very nice detail study in terms of just describing the structural importance of this structure during the Bariscan. In the south here, to sum up, we've got very penetrative fabric cleavage development, folding. We've got a transition zone just on the footwall of this structure during inversion. We get some cleavage development and shearing of that development and late folding. So it acted as a significant strain boundary. And I can go into much more detail if you wish on that. And here is a kind of a simplified 2 cartoons just showing us the kind of the sequence of events. There's our fault again, just over here. We have shortening with fabric development, and then we keep going. We have fabric development in the footwall, and then late folding of that fabric. I just want to bring in Duygu's work, and I'm not going to steal her thunder here. All I want you to look at is this section here. So when we actually go over to Mallow and we look at one of the main conductors from the MT work, again, we're seeing that high angle dipping to the south structure, which is exactly what we would have expected. One last, before I go into Mallow in detail, how am I doing this time? Okay, is the second, these cross-cutting Bariscan structures, and there's again, as it happens, there's a really nice example of this in Skellig, and it's this structure here, which is called the Blue Call Fault. And again, if we just look at this in a bit more detail, I'll just move forward a couple of these slides. We have a lovely, in this example here, dipping to the west, lovely fault core, quite an extensive damage zone, hanging wall, footwall damage zone, a nice bit of drag going on there as well, and quite an impressive breccia. A lot more contained and a lot more brittle in nature than what we're talking about earlier. Mary Ford, by the way, picked up on these back in the 90s and recognized them as well. So we're going to go to Mallow, and basically I just want to talk to you about the work that Aisling has been doing over the last few months. This is Mallow Town. Apologies again, it's not very clear, but I just thought it'd be good to overlay the geology with the geography here. So there's the Mallow Town, and I want you to, there's the fault, there's what I call the Kukkonen Mallow Fault, Killarney Mallow Fault. Don't worry about the labels. And this is a quarry here to the east of Mallow. It's a roadstone quarry. And for once, the quarry is actually sited on the fault structure. So we were very, very lucky in that we have an active quarry right on that fault structure, which gave us a really nice opportunity to have a good look at this fault in profile in a section. This actually has, since this image was taken, the quarry has gone back a little bit to the north there. It's even better in terms of what we're looking at. Just to say, Walsh, and I'm not going to go into detail on the stratigraphy, Hazelwood, so we have net reverse movement on the structure. This is the cross section. So we focused on this section up here, and we spoke to our colleagues in geography, who basically allowed us. Well, initially we did a field survey, and then we were able to produce a very nice drone survey along this section here, and then there's a turn in that. It's not that obvious from the image. This is north, so we're looking at north in that direction. There's our main fault, our Kalani Manor fault, the core zone, quite a wide core. We've got a footwall damage zone, hanging wall damage zone, as before, wider than what we've seen before. Interestingly enough, the core itself is highly karstified. We've got a lot of brecciation, obviously, but we've also got a lot of clay material in that. And this is actually from further up to the quarry. It's a very distinct clay material, which is basically choking the core zone. Obviously, that has implications for permeability. This is stuff that Mike Sims has been looking at further to the east in Kanturk, and it's a legacy. So it's a karst weathering cave deposit. This is a very quick overview of the point cloud model that we got from the drone survey. And basically, I'm going to just quickly run through some of, I suppose, the approach that Ashton has taken. We've in each case we've broken we're looking at the footwall in this example. We've broken it into a number of grids for tracing. We've traced all the fractures from those grids and basically built up a library of fracture maps for each of both the footwall and hanging wall. As I say, I'm focusing on the hanging wall here. We took those traces. She imported them into a piece of software, frac map, and basically we have a number of outputs. Obviously, this is just the strike, and obviously it's very obvious that we've got a very dominant north-south strike here. I'll skip over this for a second. This is our trace with the different nodes, different types of contacts that we have for each of these maps, and this is just what we call a density or a intensity map, just basically fractures per unit area on the map. This is an IYX diagram, and basically it's giving us a measure of connectivity, and I isolated Y abutting and X cross-cutting. And so we have a CL value here of 2, which corresponds basically to the mean number of connections along a given segment. The take-home message here is that if you're down in this part of the world, you've got a much, much better connectivity, much better as a consequence permeability, which is what we're interested in. And I'll quickly go through a few of these. And even just looking at the traces, you can see there's quite a high density. These are all, by the way, vertical profiles, in this case, footwall. So we'll just keep an eye on where this plots. Once it's below the 2 line and close to this 3.57 line, which is an optimum for natural systems. Just go back one. We can see that they're sitting decent connectivity, and as a consequence, permeability. And there's a lot of information that I'm just going to just giving you a flavor of these. So again, you see it's kind of very obvious that we have the dominance of that steeply dipping north-south fracture set. This is all from footwall. Okay, and then basically, and the data is sitting between CL2 and CL for the most part 3.57. then if we scoop to the hanging wall, and apologies, I don't have an intensity plot for that, but this is just to show you that in the hanging walls, the bulk intensity was significantly lower. We have our values, our IYX values are sitting up close to I, so these are technically isolated with low if weak permeabilities. So I suppose one of the key points we're making here is that not just in the damage zone of in the immediate vicinity of the fault, but as you move north away from that fault, a couple of 100 meters, you still have a very, very pervasive, highly quite an intense fracture network in the footwall, which I suppose it's interesting to note, and this is just a kind of an observation, that there's the quarry, we just move to the biggest cluster of warm springs in this part of the world. This is the Ladies' Well cluster, includes the spa house, etc. They're sitting quite close to the fault trace in the immediate footwall. All right, I'm going to just finish up here my conclusions will focus on, I suppose, Ashling's work. Obviously, we've got Walsh and limestone in contact with his, where we have about a net 150 meters movement of the structure, well-developed brecciated core, hanging wall, footwall damage zones. Fault core is heavily karstified, as you saw, and we've got it's choked almost with these Oligocene clay cave sediments, which are interesting in themselves. And I suppose the Cumnacrolium fault footwall fracture network generally exhibits higher intensity and connectivity levels, which hence, when compared to the hanging wall, which obviously hints at a preferred routing of fluids along that system. Okay, I'm going to stop there, and thank you very much for your attention.
Do we have any questions for class?
The question.
Oh. Question. Is there any deformation of the Oligocene sediments in the fault zone?
Absolutely not. They're so young. I don't know who we're speaking to. This is
Stephen.
All right, okay. Hi, Stephen. These are basically they're cave deposits. From what I understand, that they were deposited in the phreatic zone below the groundwater level, or in the groundwater level, I should say. Very, very slow flow rates and no evidence of deformation. Again, if you read Mike's paper, he did a paper on the two Turk quarry sites further to the west. You get some isolated crystals in some of these deposits as well. Interesting. And again, stuff that young is always interesting, as well as from the point of view of what it's telling us about things like whatever paleo environment, etc. Yeah. Rory was first, and then you, John. It's a hard call.
I was just wondering, some of the work John and JP worked on looking at Cenozoic faults. It's one of the models we have for permeability development of geothermal. Do you see any evidence of Cenozoic structures then?
I'm reluctant with considering that the guy who's sitting beside you has done so much work on them, but nothing obviously. The second fault set there, which is this what we call cross faults, which are clearly facilitating late along strike extension, and and they're bang on for Variscan and that. So my thought is that they are late Variscan, but nothing that has jumped out in terms of anything younger.
Yeah. Because geometrically they're nearly equivalent, aren't they? So if you take the alpine related things which we can see offshore within Cretaceous sediments, we know there's big faults there.
Yeah.
Then it'd be difficult to discriminate them from Variscan, because both of them are produced by north-south squeezing. Actually, you'll know Vincent Roche's work in which he's actually dating things that we thought were Variscan. Only. Well, we didn't think they were only Variscan.
Worrying me.
They've ended up, there's a lot more tertiary than kind of so.
Absolutely.
Yeah. But I wondered, Can I ask one question?
Yeah.
So I wondered, Pat, about how do you think the water has come from, given its temperature, and given that depth, how representative do you think what the rocks look like in the quarry is of what, where the water is coming from?
Let me start with the second part of the question. Because at depth, it's going to be Devonian and Devonian, sandstones and sandstones. So basically what we're seeing here in terms of the limestone story is high level. And so we're not comparing like that's fully accepted.
So how deep do you think you have to go to get the heat?
So you know what? John Weatherill has done some work, isotopic work, looking at the reservoir sources. Okay? Yeah. So we know that the geothermal gradient actually in this part of the world, with in terms of say Emma's work, and we're working with Emma actually on this at the moment, it's fairly low. Okay, so these are fairly cool rocks in comparison to certainly when you look at the national map. So I'm not going to put a figure on it, and maybe John might be in position to do that when he speaks later on. But off the bat, I'd say we're not talking about crazy depths. We're talking about maybe 3-4 kilometers. That's in terms of a source reservoir, which is still high up in that.
Still pretty deep, though.
Still deep, yeah. But those structures, I think, are significantly deeper. Yeah.
Just on the same point, very quickly. So, is it a meteoric recharge discharge, or is it a deeper basinal fluid coming up?
I'm reluctant to call it basinal because that basin in itself is now absolutely tight. So there's very, very little, say, certainly in terms of, unless it's a fracture, permeability. So my understanding, again, John is probably going to be in a better place to answer that question, but the fluids do seem to be unidirectional coming up. Whether there's a regional recharge, I don't know. I'll be honest. What's driving obviously the full cycle in terms of how that fluid is moving.
And is the plan to develop it by fracturing it more and trying to extract more water, or is it just to
obviously, when you look at, and what I didn't mention here, and I think too you'll be talking about in your talk, is when you look at and that very brief MT image that we looked at, you're getting pockets of fluid coming along the strike. Now it could be, and again, as happens in the case of say the Killarn or the Mallow structures, you're looking at lake cross structures crossing that. So you could be looking at an intersection effect there of that. So yeah, I that's all I can say on that.
Yes, so I'm going to talk about the Magnetotelluric research components of the local scale research in southwest Ireland in the Mallow geothermal area. I'm one of the co-PIs of the project. So Tao Ye, who was the postdoc of this research, so he finished his contract, and after 2 years he had to go back to China. So, but he has led the data acquisition and the data processing. Since he left, I have now taken over the basically the analysis and modeling of the data. So we have 5 work packages in this project, and I am leading the work package 3. So the objectives are to acquire new high-resolution electromagnetic data in the survey area in Mallow, and to interpret the derived electrical conductivity models in conjunction with velocity models, which will be presented by Chris Bean after me, and structural and hydrochemical observations, which presented by Pat, and John Weatherill will be talking about preliminary hydrochemical observations in the region. And the objective 3 is to characterize the conduits or pathways supplying the thermal waters to the surface using a passive deep reaching magnetotelluric method. So the deliverables are the electromagnetic database for the Mallow geothermal area, and the high-resolution electromagnetic image of the subsurface structure in the model area. And the last deliverable will be a 3D high-resolution multi-physics model of the geothermal area. Maybe I shouldn't say multi-physics, maybe I should just say jointly interpreted seismic model of the geothermal area. So Magnetotelluric, in short, MT, is quite widely used as an exploration tool in geothermal research. It is a natural source inductive method which constrains Earth's electrical conductivity, sigma, or its inverse resistivity. So we make temporary measurements of naturally occurring magnetic and electric fields at the Earth's surface, which contain information about the electrical conductivity of the subsurface. So frequency determines the depth of penetration, and of course, the resistivity of the host rock. For example, if you're in a very resistive region, your EM signals will penetrate deeper. But if you are in a sedimentary region, say in Sherwood Sandstone, like in Northern Ireland, it's very conductive, so your EM signals will penetrate shallower compared to a resistive region. So electrical conductivity is affected by rock composition, alteration, compaction, cementation, temperature, and hydraulic properties, such as porosity, permeability, and porphyry. So this is on the left, you see a typical magnetotelluric station setup, which we use in the field. So it's oriented towards the magnetic north. So we make the time variations of electric field using this, we call them electrodes, and we have this dipole. It's generally 100 by 100 meters. Where available. Sometimes in Ireland it's quite hard to get that, and because you have so many different landowners, but that's not a big deal. So yeah, we bury them, of course, all of them. So we have 1, 2, 3, 4, and 1 in the middle, 5 electrodes, and then we use these induction coils to measure the time variations of magnetic field, basically. And sometimes it's really hard to bury a vertical magnetic coil if you're in a very rocky area or so, but they are quite useful in order to understand the natural conductivity variations, not the absolute electrical conductivity. So we were so lucky for during the DIG project because we were awarded with this MT infrastructure. So we have new generation Phoenix MTU 5C systems, and we use these systems for our DIG project. And we found a great remote station for our surveys because, as Pat already showed the area, we were very close to Mallow town. So for magnetotelluric measurements, we try to be away from the noise. So we don't want any traffic. We don't want any people walking around. We don't want electric fences. We don't want cows. So we want to be in a remote area, but it's getting harder and harder to achieve this. So a remote station to clean the data is very, very, very important, which we had it in the DIG project. Anyway, so we go to the field and we acquire our data, and then we get this time series. So your electric field, so your magnetic field, and if you acquire HZ, there will be another panel here. So from these time series, we convert them to apparent resistivity and phase. So from these, we try to, by just looking at this data, we can see that, for example, for this data, we see this at the shallow, we see this relatively resistive 100 ohm meters. We are in this lithology, and then when you go deeper, so longer periods, low frequency, we see this conductive behavior in the data. So we are saying that, okay, we have something resistive, but when you go deeper, when we model the data, we should see something coming up as conductive. So once we have the data processed, so we translate these measurements to spatial patterns of electrical conductivity, and this is usually achieved through an inversion process. So basically, we're turning our data, this is our data, into a model like this. And yes, through this inversion process, we infer electrical properties of the Earth's interior from surface observations. So we are very lucky in Darius because, and also in the MT community at the moment, 10 years ago, modeling the MT data in 3D was quite expensive, but nowadays it's quite fast. And also, and there are some codes available to academic community that we could use it freely as well, which is great for us. So, of course, big MT research is not the first and the last MT research in Ireland, because it has been again widely used as an exploration tool in the geothermal research in Ireland. For example, today, as the last talk, we will hear from Jan Vozar as part of the Unearthing project. He's going to talk about the, he's going to actually jointly invert the MT data with other data sets. And so there has been some achievements, MT work done in Clare Basin and in Ratlin Basin, actually mapping the sediment thickness there. And I'm currently working also on the Leinster granite. Actually, we have some data from the Unearthing project, which was conducted almost 8 years ago or so. So during the Unearthing project, as I mentioned at the introduction, the springs in the North Leinster actually were investigated by Sarah Blake as part of his PhD at the Dublin Institute for Advanced Studies in our group. So they looked at the 6 springs in Leinster. So they are in Carboniferous limestones. So here we look at the 3D. They actually acquired very high frequency MT data. They just looked at the data up to 1 second. So basically in this region, we are talking to like the sensitivity of the data is up to 1 kilometer really. So here I'm just showing 2 springs. One is from the, this is from the area, Enfield, and this is from the Kilbrook spring. So these are the map views from the 3D MT volume, and these are the cross-section through this 3D MT volume. So the main achievements from this MT work, so they identified the structural controls on springs. So these were karstification and conduit flow in limestone, and they then also put these strike slip faults onto these models. So they also identified the Carboniferous normal faults and the estimated depths of circulation between the range of 500 to 1,000 meters. So although it's not 100%, because I think they need longer longer period data, but yeah, within the first kilometer, they are still within the Carboniferous basin. So what we did in DIG, in the previous work, they really focused on a very small area, a kilometer by a kilometer area. But in DIG, so again, so we concentrated on the Mallow area, which is the least understood part of Ireland, probably because we don't have much data over there. So discussing with Pat in order to design the survey, we actually, so this is the survey area, and these triangles, black triangles show the MT stations. We first started with a short profile actually, just to see if MT works or not. And then it was successful, and then we basically expanded our grid, and we tried to come up with a 3D grid layout where possible. Again, it's one of the challenges for us is that to get permitting. So you need to talk to the landowner, and you need to ask them to land their field to us for at least 2 nights, but it sounds stations, we had to acquire data for 3 nights. So yeah, we started in November 2021, back and forth, and then with the new generation MT systems, we completed the data acquisition. We now have 52 wideband MT stations, meaning that we are actually covering from very high frequency, 10,000 meters to like 10,000 hertz to 1,000 seconds. So one thing, station spacing varying between 500 to 2.5, as you can see, along the kilonormal fault zone. And just to the south, we try to keep the stations close to each other in order to get a higher resolution in this area. So these are some beautiful pictures from the survey area. This is the fun part after the survey. And these are our data, which we are quite happy with. The good quality data achieved almost at each station. Again, covering a wide range. I mean, it's between 150 to 300 meters to almost 5 kilometers, even more at some stations. So what we did, we just grouped the MT curves. So basically, we are in unit 1. It was from the where we have this sealed sandstone, and then we have the limestone, and we have the mudstone. Overall, it's a quite resistive area, especially within these units. But still, at depths, at longer periods, we anticipate that when we model this data, we see some conductive features, because this is what we want to see in geothermal, right? So we want to see some conductive features, basically. But interestingly as well, just to point out, this unit is actually it's conductive compared to this. It's kind of nice to see that. I don't know why, but I think I know why I looked at the past, but I can't remember. But so I modeled this data, and this is our preferred 3D MT model, and these are the map views. So we see depth slices from 500 meters to 3.3 kilometers, and these are our MT stations, the squares. And here is our kilonormal fault zone. Here is the Ladies Well, which Pat talked about. This is the Mallow town. As you can see, I mean, so the blue colors are the resistive features, and the red colors are the conductive features, and this could be due to like fluids or minerals, or it depends on where you are and what you are looking at. So what we see is that, like we see blue, like, I mean, it's a resistive area, but we also see these localized conductive features. And it's actually along this, along the kilonormal fault zone, we see those features as well, conductive features. If we look at the cross sections from these, so I took 4 profiles in the from southeast to northwest, and this is the one closest to the Ladies Well, and this was the most interesting one, which Pat just mentioned. So we see this almost vertical conductive feature, and it's bounded by these resistive features to the southeast and northwest, and this is also present in the second profile as well, although it's less pronounced here. And yeah, so and in the other profiles we see more kind of localized and lateral features, actually. Okay, and okay, you may of course ask, I mean, okay, we see this big feature which we are interested in, actually, but there are also other conductive, electrically conductive features here as well. And we were just chatting with Pat actually yesterday. Okay, I mean, what could those be? Maybe we were saying this be related to the intra-basin subordinate faults. But so to conclude, we mapped steeply dipping structures which represent early extensional basin faults. And these conductive structures could be associated with fluids or a proxy for highly brachiated or fractured permeability associated with damage around the faults. Of course, the work is still ongoing because we have the publicly available TELOS frequency domain airborne EM data, and which we would like to use to calibrate the shallow structures in the MT model. And we would like to jointly interpret our MT model with seismic gravity and also with structural geology and hydrochemistry results. Thank you.
Okay, thanks a lot, Duygu. This is Mason Reservoir's work. He worked on DIG. Mason moved on from the project quite recently, and he's working in industry now. And he thought he was going to be able to come today, but they have something on and he can't come. So I'm just stepping in to give a talk. So he prepared all the slides and everything. So we're interested here in the shallow part of the structure. And we're trying to characterize it, and you can see with the magnetotellurics, you can see difficulties you have when you're trying to characterize shallow structures. We saw passive methods, seismological methods earlier today, and we saw great outcomes, the work that Emma showed and the work that Sergei showed. So depending on the scale size of interest, that really determines what sort of approach we should take. So let me just kind of distinguish between what we call passive seismic and what we call active seismic. So in active seismic, typically, say, reflection seismic that was developed or really pushed in the oil industry, that was the first big data, one of the first kind of big data sciences that existed in the world. So back in the 1960s and 1970s, the reflection seismic community were the second biggest users of the old magnetic tapes after the American government. So this is a really early adopter of big data. And as geoscientists, we started to think that this was normal, but this was actually abnormal at the time. This was an amazing drive that was on. So if you want to image the top 2 to 3 kilometers of the crust, and you have the money, then and you want to do it, you want a seismic image, then shoot active reflection seismic. There is no question about it. If you have the money, that's what you should do. And because you're not going to better that, because you have such a high data density that you've got all the processing flows that have been developed for the last 40 years. That is the right thing to do if you want to see the best images you can get. However, it's very expensive. Rory was telling me today that, typical mobilization cost could be 120,000 euro, and it's of the order of 20,000 euros per line kilometer. So it's expensive, but if you have the money, that's what you should do. So what we're trying to do is, this is more like a test in this area. So that's active seismic. So that's where you go out, you put out your sensors, you shoot. Shoot, in this case, on land means you vibrate a truck. It moves along as a source. Passive is you put out your seismometers and just let them record, and you see what comes in. And that can happen at multiple different scales. So from the sort of stuff we saw today that Emma and Sergei showed, they're using teleseismic earthquakes, and they're using surface wave analysis of teleseismic earthquakes. We can also do this at a much smaller scale and record traffic, ocean waves, and they generate background noise, and that background noise can be actually used to image, but we're not injecting the signal ourselves. These techniques do not have the same resolution as reflection seismic for multiple reasons. The sources are not strong enough, the frequencies are not of the right order, the sources are not stable enough in time. There are a whole bunch of reasons why you just do not get the same quality images. So you can see that all of this is a kind of expectation management piece of the conversation. When you put out these passive seismic stuff at shallow scale, you're not going to get the same sort of images you get in reflection seismic active, but it's a hell of a lot cheaper financially, a hell of a lot cheaper. So it may be a good prelude, something you do before you go and shoot seismic if you want to spend your money in the right place. The other issue is that passive seismic work well at a big scale. So we saw it this morning, the kind of big scale stuff we saw with Emma and Sergei. It works really, really nicely. The top 2 kilometers is the antithesis of a sweet spot for passive seismic, because you can't get down to the depths you want, except with using low frequencies that are coming from the ocean. And when you use those low frequencies from the ocean, you've got very poor resolution because you don't have them. You don't have the right high frequency data you need to give you images of small scale structures. So it's definitely not the sweet spot. But I'm going to show you what we've been trying to do and what might be possible. There are a few positives that come out of it, but it's certainly tricky. So with a limited budget, how can we use seismology to image the top 2 kilometers of the crust at a reasonable resolution? Reasonable resolution means that we can see something that might bring us to maybe go shoot some reflection seismic or connect to other geophysical methods, or connects to the broad scale geology. Okay. And I've said already, you're not going to get the same sort of images you get when you shoot reflection seismic. And I'm kind of repeating myself here. I think these are a good start or a good prelude. Okay, so we're working in the Mallow area, and we have applied 2 methods in passive seismic imaging in this region. And this is Ladies Well here again, just to keep your eye in. And the first method we put out 99. There's nothing specific about 99, but we had 99 5 hertz nodes that we put out at 50 meter spacing going north-south across the structure. And we left them there for 11 days. So these nodes, I'll show you pictures of them. They're basically just standalone geophones, and we put them out, and we just put them out and leave them there. And I'll come back to the sources we use for that. And then, originally we thought we might try to get down to a kilometer with that. But then when we were talking to Pat early on, Pat's going, I really wish we could get more information deeper than what you can get with these nodes. And we thought, well, that's going to be tricky. We're going to have to do something completely different if we try to do that. And then as an add-on, we put these extra few instruments out here. They're broadband seismometers, and the nodes are at 5 hertz bottom, the lowest frequency. They can actually go down to about 1. But these guys record much broader frequency range. And we left them out for the goods of a year. Well, they've actually been out for 1.5 years. I'm going to show you 9 months of the data that we used on those instruments. And we're using a different method on that I will come back to. So when we put out the nodes, we thought, okay, you need ambient noise. It's passive, so you put the sensors out and you go, okay, where's the noise coming from? So you can do a noise analysis. In fact, we did another thing. You can put out clusters of nodes first to just test where the noise is coming from and what you've got, what's available to you. So passive seismic really depends on what's available to you. And the things we looked at, we thought maybe we could record quarry blasts that didn't really work very well for us. Local roads, the noise wasn't strong enough. The river, there was some noise from the river. Maybe that could be used. Mason thinks that Mallow is a city, so he called it Mallow City. And then you've got the railway track, which is interesting. And then we also have teleseismic earthquakes. These are the waves that are coming from earthquakes from very, very far away, and maybe they could be used too. So these are all the possible ambient noise sources. Why is this stuff cheap? It's cheap because you basically go out, you install the sensors, and you just walk away, and you leave them there, and you let them record for as long as you like. You connect them to a battery if you want them to stay longer than a month. So that's why it's cheap. It's very easy in the field, and that's what you do. So this is what it looks like. So the sensors, we decided in the end, the best noise field was actually the railway line. So we installed sensors 30 meter spacing all the way along the railway. And we used the train as the source. Why did we use the train as a source? Because if you think we want to get down at high resolution to a kilometer, then we need a strong source. If you see in engineering, they just go and use a hammer, it gets you down to a few tens of meters. That's not good enough. If we go and use the ocean ambient noise for the top kilometer, the wavelengths are kilometers, so we've got absolutely no resolution. So it's this antithesis of a sweet spot. You've got to do something different. So the train is a brute of a thing that goes flying past every so often, and we decided to use that as a noise source. And these other guys here, these are the individual broadband seismometers that are out. We left them out for a year, and I'll come back to what they were doing later. And this is what the notes look like. Okay, so what we did is we used a thing that's used in engineering refractions or seismology, in engineering seismology. It's absolutely standard. And this is based on surface wave dispersion analysis. So ideally, if you want to see really sharp boundaries, you should use body waves because they go down, they hit the boundary, eventually they come back again. But you can, at that very small resolution. But you can also use surface waves. And surface waves basically disperse the different frequencies or different travel at different, or the different wavelengths in the data, and they're traveling at different speeds. So you can actually get an estimate of how the velocity is increasing with depth, because the longer wavelengths actually go deeper into the structure. And you look at how they disperse, how they travel at different speeds with different distance. So instead of having a hammer, we basically have a train. And I'm going to cut out all the details about how we cut out the train data and all these tests about the wheels of the train and how the different wheel sets, how far they are apart, how that affects the data. I'm just cutting out all of that and just showing you a kind of a raw image, which is the outcome of all of that work. So the reason this is in orange is because we have no resolution down there. But when you look at what's called the sensitivity kernel, so how sensitive the data are with depth, you basically have no sensitivity below here. So with the train and the surface wave dispersion analysis, we can actually think we can get down to about 1 kilometer. So here we are south, we're moving north. This is the fault zone here. And then what we can see is when we move across the fault zone, you get extra basal heterogeneity that's sitting on the footwall, which makes sense. And you can see that in the geology. And you can actually see there's a lot of variability here in this footwall. So in a sense, you could think of this variability in some way as, I know it's lithological, but that will be associated with some structural features that are allowing you to excavate at depth on this side of the structure that's not really available to you on the other side of the structure. So I know that for people that are used to looking at reflection seismic data, this looks incredibly disappointing. And of course, it is, but it only costs a few euros to collect. So, but this is what you get from this sort of data. So nothing surprising in the sense that this is more heterogeneous, but it does give us an idea where these structures are going to, and they are excavating to quite some depth. So then the question with Pat said, hey, can we see anything below 1 kilometer? The answer is with this method, we can't. So we're going to have to do something else. And for that, we test. This is just a test. We put out these 4 broadband seismometers. And for the broadband seismometers, we used a different technique called receiver functions. And essentially the idea is that if you have a station here, and you have earthquakes, teleseismic earthquakes that are very far away, the waves are coming from the earthquakes, and then they're turning and they're coming up into your station like that. And as they hit boundaries in the subsurface, the P waves get somewhat partially converted to S waves. It's like you trigger a new S wave at each boundary, and you actually get information directly below the station. Now, traditionally, this is used for crustal scale stuff like looking at the MOHO or mid-crustal reflectors. But we actually were able to use it up to 6 hertz spectral frequency, which is very high for receiver functions, but that information was still in the data. And that allows us to look in the very upper part of the crust and get some information from it. Okay, so these are the earthquakes typically. So here's Ireland at the pole of this polar diagram here, and these are the earthquakes that are used over a 9 months. We're not 100% finished with this or with the previous image I showed you, and there's still another 6 or 8 months data to actually bring into this analysis, but I'm just showing you the initial result from it. So remember, we're here. There's a lady's well. These are the structures. And we were actually quite interested and surprised with this. Remember, this is a probabilistic approach in the sense that you can run multiple models to get an estimate of what the structure is, and you get your mean model, which is the dashed line here, and you get your uncertainty. So there's, we're pretty confident that these are pretty good results. The other thing is that these are independent. So this is dig 1, 2, 3, 4 at the top. So that's going 1, 2, 3, 4. These are basically independent measures in the sense that each station is treated independently. So the fact that they kind of look similar really tells you that there is a lot of something structural going on there. So the main thing we see, this is the S-wave velocity with depth. Here's 0 to 8 kilometers. So at about 3 kilometers, at the top, we see what we expect, increasing velocity. But then at about 3 kilometers, we see this significant decrease in velocity at about 3 kilometers depth. So the initial thought was, of course, maybe this is some sort of fracture structure, or, you know, that will be maybe one's first thought. So then we thought, okay, let's do just a tiny bit of gravity modeling and see what we can get from this. So you take this profile here. What we did was we took the DIAS National Gravity Data Set. It's not at this higher resolution, so we had to reinterpolate it into this region here. And that interpolation brings an uncertainty penalty, and that penalty is shown in the width of this purple or this pink thing here. The width of that band is a kind of like an error bar associated with the fact that we have an interpolation. If we had more and more real data without having to interpolate a field data in this, then that band will collapse. However, you can see that there's still signal in it because the band is smaller than the height of the anomaly. So we can trust this pink thing, the interpolated data, as giving us some signal. And then what we do is we take this body. The good thing about the seismic is this is kind of like a reflection seismic method in the sense that it constrains the boundaries between the bottom and the top. Often in gravity modeling, you can see the top fine, but you don't have any idea where the bottom is. So here we can constrain the top and bottom. So we just literally take the velocities in here, and then we use Gardner's equation, and we plug in a density that we expect, and we just put it sitting where these sensors are, and we have a contrast with the surrounding material, and we get a really nice fit. And it turns out that that this here has about the density that you would expect for some sort of granite. So it looks like what I called a granite lens, but I should have, I guess, called a granite laccolite that's sitting at about 2.5 to 3 kilometers depth, and it is approximately 3 kilometers long. And this is in a north-south direction. So this is just a cut in a northwest-southeast direction through this structure. So I think combining these things, there's more work to be done here. This is just a taster. But combining this, we were quite surprised at what we got from receiver function. This is one of the cheapest things you can possibly do. Put a seismic station, you just have to plan ahead. You have to leave it for a year, then do this analysis, and you get some really nice it's almost like a 1D borehole with a kind of broad scale sonic log in it. And you can drill as deep as you like. This is 10 kilometers deep. Okay, so some comments on this. So very cheap passive methods are capable of detecting important features in the top 5 kilometers. It's important to jointly interpret with other geophysical methods within a broad geological framework, of course. And we're suggesting that this can act as a guide for the location of what are very expensive but very, very effective reflection seismic surveys that bring significantly higher resolution. And we, again, another local suggestion here in this geographical area is that we might have seen a small granite body near the Killarney Lava Fault zone. Thank you.
So our last talk on the local scale research will be given by John Weatherill on the hydrochemistry studies in the Mallow region. Thank you, John.
Okay, so thanks everyone. Thanks, Duygu. So fortunately I can't be there today to present, but it's great to be able to dial in here on Zoom. So I'm just going to give really an interim update on the hydrochemistry program, which started this year. So it started at the start of July, and we've been kind of going at it full swing since then. And I think I've got enough results really to provide some insights into the hydrogeological functioning of the Mallow area. And with some good questions earlier on from the audience, which I might be able to address in this talk. So I'd just like to acknowledge, I suppose, people that have been helping on this part of the project. So Amelia Pedinius, PhD student and field support. Ji Quishi is an analyst here in UCC, and also Noila Onadir, who was helping us out with the field work as well. So the hydrochemical program really is, I suppose, it's a characterization study at the end of the day. We want to kind of look at different hydrogeochemical parameters and also hydrological parameters for the, I suppose, the main Mallow study area, and also the wider Killarney Mallow fault zone and the general, I suppose, part of the general study area. And I'll mention a few other sites as we go along. So we've developed a groundwater monitoring network, and we've started sampling on a bi-monthly basis, so twice per month. So we're hoping to do 12 rounds altogether from 8 different sites. So we've kind of devised the sampling program based on a selection of thermal sources and also a selection of non-thermal or reference sources, the vast majority of which are springs, which are the non-thermal sources will be associated with sort of normal shallow groundwater within the region. So we're undertaking a physicochemical, so that's measuring temperature and things like that in the field, and a detailed hydrochemical and analysis program. To look at, I suppose, small amount of temporal variability. We started sampling in July during a period of base flow recession and groundwater recession. And now we're starting to move into the recharge period of the year now. So it should be quite interesting to look at the, I suppose, the variability in the chemistry of these springs as we move into the winter period. And that'll keep going from July till the end of this year. So we're interested in the composition of the deep thermal reservoir migrating to the surface in the form of Ladies Well and the Mallow area. So we're looking at, I suppose, a range of chemical parameters, so major ions, and also major and minor trace elements, and also some very useful, I suppose, techniques or tracer approaches. So we can use rare earth element fractionation, for example, to look at different hydrological and water rock interactions along the flow paths. We're also working with Carlos Roche's group in Trinity, who have a new isotope analyzer, and we've been collecting water stable isotope samples as well at the same time. So with the water isotopes, we can look at the contribution of relatively recent recharge, and we can look at then how the deep reservoir composition of that stable isotope relationships and how that fits into our overall conceptual model. So we'll eventually feed all these parameters into a multivariate statistical model, so principal component analysis or something like that. But we also want to have a look at actually trying to date some of the waters as well, because that's never really been done before in Ireland. So I'm going to work with a specialist laboratory in Germany. So I'm going to do tritium dating, which is useful for recharge that's taken place since sort of 1950 onwards, and also carbon-14 based on DIC, which dissolved in organic carbon, and that's suitable for much older water. So that external lab is going to do some modelling for us, and hopefully we can get a realistic range of groundwater ages. And hopefully that'll then feed into the overall conceptual model based on, I suppose, insights from the geophysics, particularly from the MT work that Duygu mentioned earlier. So this is our monitoring network. So my geology map isn't very good, but you can get, that's the general study area you've seen before. So these are the springs that we've been targeting for sampling. So the CS there, that's a cold reference spring. So CS3 in the west there is a public water supply from Mill Street. And there's also EPA monitored wells as well, which are monitored for the Water Framework Directive and have a long-term water chemistry data set going back to about 10, 15 years. And then in the Mallow area itself, so the TS1 there is the Ladies Well. TS3 is a public fountain. Unfortunately, we couldn't get access to the spring actually in the Spa House because it's since 2022 it's been sealed off for radon abatement purposes. I asked if we could drill a little hole in the capping unit on it, but they weren't keen on that. So on the left-hand side there, you can see that TW1. So this is a geothermal borehole that was drilled in the 1970s, which is pumped and supplies heat for the Mallow Municipal Swimming Pool. So we're able to get access to that in the plant room. And just to kind of give just a range of temperatures that we would see here. So this is from data for the last 5 sampling rounds. So typically the Mallow sites there, the temperature is relatively constant. between the three locations, so in and around just under 20 degrees. There's also a very interesting geothermal feature to the northwest of Mallow there. So TW2 is actually a public water supply borehole that was drilled in the early 2000s down to 40 meters, and it hit hot water about 25 degrees at just 40 meters below ground level, quite close to Mitchelstown. So that was something we absolutely wanted to include in this program, because it's an example of a separate geothermal source, which looks to be tapping a deeper reservoir within the Mallow area. So we included that as well. And then the other sites there, so these are the three reference springs that we've been sampling. So that's CS's Cold Spring, and these are all actually all holy wells, which are local and typically have slightly warmer than normal groundwater temperature, around 11 degrees. So just show you what they look like. So that's Lady's Well there on the top left. So it's essentially a pond which flows out then into the down as pipes out and eventually flows into the River Blackwater. There's a public fountain there, so that's what's called the Lion Heads locally. And the thing there on the left is the swimming pool. So this is borehole is actually in the basement of Dunstore's car park in Mallow, and it's piped underground, pumped and piped, I think a couple of 100 meters, and then goes through a heat exchanger. That's a little diagram I've copied there. I don't know if you can see that. That's actually on display in the swimming pool. Goes through a heat exchanger and then is used then to heat the swimming pool. And of course, there's a mistake, if you can see on that diagram there, because it's claiming that sunlight is being used to heat the water, when of course it's geothermal heat in that source. So these are the cold reference springs. So Tubbard Well, it's a large, beautiful holy well. It's a public water supply. That's in Mill Street along the Killarney Mallow Fault. And then the two reference springs there, these are again holy wells, which are kind of used sort of locally, moderate, maybe relatively low flowing springs. So just to look at the overall chemistry, so this is a Piper diagram. This is including our samples, but also the EPA monitored springs in the area as well. And they all broadly plot within the kind of the right-hand corner of this Piper diagram, the summary diagram in the center. So this isn't indicative of, say, for example, deep geothermal fluids or anything like that. It's essentially similar composition to the shallow groundwater. We don't see much difference in terms of the overall major ion chemistry. And the dominant influence there is dissolution of carbonate. So we see calcium and bicarbonate would be the hydrochemical type. And there's very little variation in terms of both the thermal and non-thermal sources. The slight increase in fluoride for the thermal sources, so 40 to 90 micrograms per litre, and a slight increase in bromide. So these are sort of components that we might associate with sort of deeper fluid circulation, maybe brines, etc., paleo seawater or something like that. But they're only slightly higher than the surrounding cool groundwater. The thermal sources are generally less mineralized, so their conductivity is about 470 versus the non-thermal, which is around 578, 600. So interestingly, even though the water is inferred to be much older, it's less mineralized than the surrounding shallow groundwater system. So just some kind of back of the envelope, just regression analysis, looking at some of the parameters against temperature here on the x-axis. So just picked what correlated quite significantly. So sodium correlates quite significantly with temperature between the thermal and non-thermal sources. Silicon, quite significantly as well. Okay, so sodium is usually associated with ion exchange processes, and silicon or silica is a good general indicator of bulk water rock contact time. But the really interesting one was magnesium, which is very highly correlated with temperature across all of the samples, and that suggests possibly the influence maybe of dolomitization on the chemistry of the thermal waters, and so magnesium really was the main interest there. And of course, that's would be associated possibly with dolomitization. Okay, so just did some preliminary geothermometry then, looking at, so these are our geothermometers based on the assumption of an equilibration with a mineral phase at the deep reservoir, which then migrates back up to ground level or to the discharge point, where the water is assumed then to be equilibrated at depth. So there hasn't been re-equilibration during the ascent phase back to the ground level. So for the mallow cluster, then based on quartz, okay, so it's meant to be suitable for higher temperatures, but tends to be less prone to re-equilibration during the ascent from depth. So the typical reservoir temperature of around 40 degrees. There's some issues, variability in the silica concentrations in the Ladies Well, the blue circles there for some reason. Not quite certain why. But most of the mallow conduit or the mallow group tend to plot around in and around a reservoir temperature of about 40. So chalcedony can be used as well. It's a cryptocrystalline form of quartz, meant to be better for relatively lower temperature reservoirs, but is much more prone to re-equilibration. So didn't really produce a meaningful result there. The mallow springs give the same reservoir temperature as the recharge temperature. So that's almost certainly impacted or affected by re-equilibration during transit to the ground. So just the other potential geothermometers that we can use. So there's a whole range of these, and they're kind of blunt instruments in certain ways because we need to take into account various other factors, and we just at this stage don't have the chemical data, so we need trace elements and things like iron and things like that to improve the estimates. But the calcium magnesium and the cation geothermometer looked quite interesting as well. So it produced then a higher reservoir temperature around 60 degrees, and also a higher temperature also for the Johnstown well as well. So it's quite interesting. The Johnstown system definitely seems to tap a similar but deeper geothermal reservoir, and just again, just using an assumption of 25 degrees Celsius per kilometer, and with a 10-degree recharge temperature. The formation depth, so this is basically the bottom of the flow, the convective cell, if you like. So what we're assuming here that the water in the springs is relatively local recharge, for whatever reason migrates to a considerable depth, and for whatever reason to do with the hydraulics, it migrates rapidly back up to the surface then where we see these springs. So the conduit then for quartz, which kind of gives a reasonable estimate for the mallow system, is around 1.2 kilometer depth. That kind of agrees with some of the previous work that's been done. In the Johnstown, a little bit deeper, down to 2 kilometers. And then the potassium magnesium geothermometer then, so it's a slightly different approach. Then it gives a significantly deeper formation depth of 2.3 kilometers for mallow, and then 2.5, only slightly deeper then for the Johnstown source. So that's really just, I suppose, wanted to share really with the workshop just some of the insights from the hydrochemistry program. So it's ongoing, and we've got a lot more sampling to do and a lot more analysis to do before the year is over. So just some kind of concluding remarks then. So the thermal and non-thermal groundwater ion chemistry is really dominated by carbonate dissolution. So unlike, for example, Sarah Blake's work in the Leinster Springs, we don't see evidence of sort of saline conditions or brines and things like that. This is effectively relatively local groundwater that's migrating to a considerable depth. So the mallow area, kind of linked to the MT works, there seems that chemically or hydrochemically, all of the sources within the sort of Spa Glen area are very, very similar and have similar temperatures. So we assume then that this is a single conduit system supplying these springs and boreholes. The Johnstown well is very interesting. It's a 40-meter depth borehole with 25-degree water. Appears to tap a deeper part of the same geothermal reservoir. And that's certainly an area for follow-up work. I'd love to get stuck in there with an air rotary drilling rig and see how extensive the warm water is. Was it a case of hitting the needle in the haystack when that well was drilled? Or is it quite extensive in that structurally complex area? So that's certainly for further work. And then some of the geothermometry then, as I said earlier, around 1.2 to 2 kilometers based on quartz, and a little bit deeper then for the based on the cation geothermometry there. And both geothermometers suggest then that the Johnstown is a deeper reservoir. And assuming, as I said, a recharge temperature of 10 degrees and the geothermal gradient of 25 degrees per kilometer. And yeah, as I said, everything's ongoing. We're going to keep sampling and analysing until the end of 2024. Okay, that's it. Duygu, that's my update. I'll take any questions.
Thank you. Our first speaker is Jan Vozar from Slovak Academy of Sciences. He's going to talk about geothermal assessment with an integrated joint immersion approach and its application to Loch Ness Basin, actually. Thank you, Jan, so much.
Thank you very much for the invitation to this workshop. In this talk, I would like to present some older results from Artem project, and we are continuing with some new modeling with same data. And I was former postdoc on this Artem project. That's why I'm still working on it, and now we are continuing in some geothermal assessment with an integrated geo-energetic approach. I will explain this. Talk is more about methods and 3D inversion approaches to how to really combine several types of geophysical data and what kind of advantage we can get from it. And so I will present some primary data like Google anomalies analysis, preparation, and some independent magnetotelluric modeling. And then in final, I will show what we are getting from geo-inversion, what is the advantage, why it should be used, particularly in these geological settings. And of course, then in final step, I will show some simple assessment of geothermal aquifer in this area. So area is Loch Ness Basin. It's in the northern eastern part of the Ireland, and just simple geology. That we are working over area where the Thermotriassic Loch Ness sediments or sandstones are situated. And what is important on this Thermotriassic Loch Ness Basin, that is contained, it contained one layer of depth about 1 to 3 kilometers. It contains Sherwood sandstones, which are very well known for, and are an example of a deep permeable sedimentary system which can hold geothermal aquifer. So another reason why we selected this area that we have very good geophysical data coverage of Loch Ness Basin area, which is situated north of the lake. And we have over 120 magnetotelluric sites. We have 3 boreholes there, and we have also very good coverage with gravity primary data. So here is also example of lithology from one of the boreholes, where we have quite a layer of basalts on the top, and then limestones and sandstone below, which causing sometimes problem for some geophysical data. And why we are showing this is that with combination of all these data sets, we like the improving resolution of magnetotelluric method, improving resolution of gravity modeling, and it also improved the later showed assessment of geothermal. First, we also use not only empty data, but we also use this today mentioned TELUS dataset of airborne EM data, which we use as for correction and checking for empty data whether they are not noisy particular points, and we from the measurements we are able to reconstruct very first shallow structures by 1D models, and then recreate responses for 3D magnetotelluric data, and we could check. We can see that these stars are from airborne EM data, so 4 periods that they are very well fit to our sounding curves response function of empty data. So they can be used to replace the shortest period or remove some noise or some not correct data. And second database which will be used in this joint version is Google anomaly data from the area. It's a combination of local measurements and regional one. And we did some kind of, we have to process them slightly before to remove sharp anomalies from shallow structures. That means we apply some shortwave filter and long-wave filter to just focus on depths about from 1 to 8 kilometers. And what is important here that before I said that we have also, I didn't say that we have very good reflection, we have also seismic reflection data from this area, which unfortunately are used just as a visualization of the results because they are just 2D, and with this reflection data they have also provided some velocity models, but they are really unreliable. And simply when we are doing 3D modeling, we can't really extend this kind of seismic information on at least part of the area as a 3D information. So most of the time you will see all the time now profiles where we have these seismic reflection models over some conductivity models or density models. Yeah, that's first just shortly that I would like to show that how important is 3D, that really the 3D improving the resolution and also better reflecting and better correlating conductive structure with the seismic models and also with borehole data and logs. And why I'm showing this presentation is it's all the presentation is about the GeoInversion, and there is several codes which can be used for GeoInversion, but in these models we are using Max Moorkamp's GIP3D, GeoInversion framework, which is capable to GeoInversion of not only MT and gravity data, scalar and tensor, but also magnetics, electrical resistivity tomography, and surface, which is more or less covering quite a lot of all geophysical models, which can be get, and also seismic data from the beginning based on first travel times. And what is important on GeoInversion code is how we are coupling these different models. This means we have empty data, we have gravity data, we are doing inversion, but how to do it, like we are coupling between these two models, that it's somehow they are sharing information between each other. So normally, for example, in leap mode, there is a way that you have already a leap mode or IGMAS codes or geo-analyzed. You are creating some geological model and units that each has some own parameters like conductivity, resistivity, conductivity, and density or seismic velocities, and these are then modeled on the surface. They're giving some responses on the surface, and we can compare it with measured data. So in our case, we don't have a unit or module or unit where we're setting certain parameters. We have to force the conductivity model and density model to be similar. And it can be done by different way. And this code has two approaches. First is based on cross-gradient method, which is more or less forcing the anomaly shape similarity. That means if we it's this function there, it's just telling us that if we have, for example, ellipsoid and sphere, that it will create this kind of responses. And we're trying to minimize it when it will be two spheres, that these vectors which are here, they will be zero. So they are not looking in direct relation between the density and conductivity. It's simply forcing to each model similar shape of the anomaly. And it's ideal case for power measurement in Lochner, because we expect that we have water bearing layer which is very conductive and less dense. Of course, there is another method. If there is not such a clear geological settings, we can use a variation of information which is based on machine learning. And this code is simply trying to find data points which has some kind of relationship and force it to the model. So why we are doing it? Everything, it's because of this is typical example how the conductivity model was improved. So on the left is geo-inversion, on the right is empty-only inversion. A typical problem of empty models and conductivity models is they are not very well resolved. The bottom boundary of conductor is not very well resolved. It's smeared by numerical regularization, and we can get very sharp bottom boundary of conductor most of the time. But in this case, with combination between the density and conductivity model, this combination coupling force bottom conductor boundary much higher, and we have even 2 layers in this part of the model. So much better resolution. We can estimate also how the coupling was working in the area. So there's a cross gradient module, which showing that, for example, not very well correlated conductivity and density model is in the southern east part of the model. And these models were shown. There is like a 3D visualization of, on the left is conductivity model, on the right is density model. They are quite sharp. It's really like in narrow layers. They are smooth and improve, particularly gravity model without conductivity model, just gravity only inversion can really get this kind of layered anomalies because it has very strong problem with the vertical resolution. So there's another line which is going from the north to the south. It's preserved all this layer in the whole area, and this is like 3D visualization of same model. And we also continuing with the modeling by cross gradient, but we are using also this variation of information coupling, which is quite good for the areas where the similarity in the shapes are not so well preserved. So this is just in work in progress because it's creating even more sharper and really like this model seems like a sharp boundary models that probably it's more or less time. Now we are testing the parameters to improve this variation of information coupling models. What we can get from this more precise and more better models for models with better resolution and better coupled density and conductivity models are more precise cross plots. Now you can see the cross plots of models with triangles and borehole information cross plots. They are completely like not identical, but where the correlation is very good, and that's why we can really then use it for estimation of porosity and permeability. We are using some stochastic code from Campagna et al., which can produce cementation factor distribution, probability distribution, and also porosity. This is simplification because I'm not into petrophysical modeling, but I just try to finalize this model in some kind of geothermal assessment. So there is no like a clay calculation, but even with this simplification, we get quite similar permeability for both boreholes, which can later be used for simple estimation of heat capacity in the area. So they use this simple formula. And on the right, you can see selection and parameters which were included as input, and they are extracted from my geo-inversion models of conductive and density models. And what we got from it is just some kind of geothermal aquifer estimation, lateral changes within the area. that what can be expected based on conducting model, based on density model, what is the heat capacity distribution in the area, lateral one. So conclusion is that GeoInversion for particular geological settings, bringing better resolution to density and conductivity models. This better resolution resolve better this water bearing layer of which is correlated with sandstones, and then we have better cross plots which can be used together with the borehole data logs, and then we getting better porosity, permeability estimation, and better information about the geothermal potential of the area.
Now, our first speaker is from GFZ, Ben Norden, and he's going to talk about cross-scale characterization of the subsurface for sustainable geoenergetic utilization. Thank you, Ben.
Yeah, thank you very much, and hello to everyone in this room. So I started with a slide showing you a little bit the German perspective of experiences with utilization of the subsurface for geoenergetic projects. And there's a nice image which I like to see on the one side, like this Minecraft picture or image from the subsurface, which is very nicely showing us that we, in most cases, are dealing with an underdetermined subsurface. So we have just some information, and every model we do, this is somehow underdetermined. It is missing something, but we want to put in the most relevant properties and processes. And what you see on the right side is this Lego-like thing for geothermal applications, which is the view of an engineer in the program. So he just wants to have some numbers from the subsurface that he could design something properly and get it run. And somewhere in between is geology, because we need to discuss with the different people and to find out, okay, because we are also dealing with an issue that we are not doing hydrocarbons. So hydrocarbons may perhaps sometimes the benefit that you can spend a lot of boreholes without success, and then you have one with success. But in geothermal, you need to argue to find a new investor if some project fails. And we made a lot of experience like this in Germany as well. So that's a part of what I want to talk about. So the targets are manifold for us. So you see a screen like or a sketch like this. We see all the different targets in the subsurface, going from storage, aquifer thermal energy storage, hydrothermal reservoir utilization, or even petrothermal systems. So what is possible? Back to also nuclear waste storage and things like this. And this is for us in Germany, it is really the kind of game changer, because we need to discuss what to do with our nuclear waste. And in this context, the data of the subsurface is now becoming available for the public, because we agreed that we would like to have a very clear and understandable process how Germany will decide where to put its nuclear waste. So this needs to be understood by everyone. And then they said, okay, the data of the subsurface could not be held by companies anymore. So this is a major change which happened a couple of years ago in Germany. But if we go for all the targets and we want to use them sustainable, so responsible in a way, different than we did in the past for hydrocarbon, so we need to think about some issues. Geothermal as well, so how is our system, in which kind of system are we working, how is the production rates, the recharge, what is the system behind. So what might be impacts also by utilization of geothermal energy. Same for aquifer thermal energy storage. And with So, especially if you go to systems which were very old, so maybe of more than a million of years in equilibrium, and we just want to change some thermodynamic properties, like extract the temperature, what will happen with the subsurface? What is going on? We need to consider this to be a better player than in hydrocarbon. So, and the same, of course, is also for underground storage. If we introduce some additional heat by nuclear waste or whatever. So what all the projects have in common, we need some information about the subsurface. And at least we need some information about the general setting, the thermal setting, the heat flow. So we would like to know what is the heat supply of the Earth. We would like to have the temperatures at depths. Therefore, we need the heat flow, we need the structural setting and the composition of the structure. And of course, we need then the properties, the rock properties. We need them in terms of mineralogy and chemistry, but also in petrophysical properties. And of course, we need what is in the pore space or in the fractures. So what is there in fluids? And we need to know some hydraulic properties and the productivity if you go for geothermal. So this also we need to get some idea what might be the interaction of any utilization of the subsurface. But the nice thing from a geological or from perspective of a geologist is that all these parameters are somehow related to geology. So they are subject to fundamental geological concepts or controls. So understanding the geology is essential if we want to establish sustainable and safe utilization of the subsurface. So this is some parts of the points here summarized in this characterization across scales, because the across scales does not only mean that we are coming from very pore space or some micro scale to macro scale. It also means that we have a time issue. So not only spatial, we have also a temporal scale. And we heard a lot today about geophysical data already. And from a geologist's point of view, geophysical data is always indirect data. And we experience so often that it's necessary to get understanding of the real subsurface. We need direct data. Most projects where we have some failures before were because we think there is something based on the geophysical data. So there's a kind of side development, and the characterization doesn't stop. If you think now you have characterized it, start the project. No, at that point you start really understanding what's going on, and you need to identify what are the relevant properties and processes. And if you start with geothermal projects in Ireland, you will realize that some things will come together and you will learn. And so do not be disappointed if one of the projects will fail again. I would expect that something like this might happen as well. So, and you see, but this is where my focus is in terms of drilling. I like drilling. I like to get the information on the drill site. I like to interpret the data with co-log integration to get it to get this in another scale, in the borehole scale, and then to see, okay, how does it fit to the field data, to hydraulic properties, and can I get an understanding of the reservoir behavior in the field scale. So one step I mentioned, or one thing I mentioned was the heat flow, and I would like to share with you some experience we made with the heat flow data of Germany. And you see here on the left-hand side, this is the data stored in the global heat flow database, and we did evaluation of this data because heat flow seems to be very simple, but it's a derivative measure. It's determined by a temperature gradient and the representative thermal conductivity. So you need to know how it is determined. And we just revised the data, and you see how many from the dots are left, where we think, okay, we can understand what the people have done. So all which are rejected are in let's say are not really scientific, because we cannot argue on the quality of the data. We do not know how they were determined. And on this slide is just made a small figure of the heat flow data of Ireland. And so where you see it, some green circles around this, they were not corrected for paleoclimate effects. And paleoclimate effect is highly relevant for Ireland because you see just here, most of the boreholes are from less than 500 meters. So for me, it's also interesting to say, okay, it would be nice to go to greater depths in Ireland to get some better information how maybe heat flow looks like in 2.5 kilometers depth. But interestingly, the temperature, the heat flow range is between 70 and 85 milliwatt per square meter, and yeah, this is you see here in the same. Oops, almost too fast. In the same range like for Germany, so we have a low entropy setting in both systems. But now I would like to share you some information about the North German Basin. And here you see a simplified geological cross-section. This the huge basin from England to Poland, Permian Basin, and you see we have more than 6 to 7 kilometers of sediments. And a feature in our basin as well are the salt structures, and they are also highlighted here. We have a lot of salt structures, and they influence the structure of the subsurface and the layering of the sediments in the subsurface. And I will now just touch some of the projects listed here and some of the main experiences we made. So one is the former hydrocarbon exploration well in Großschönebeck. It was meant to establish as a deep geothermal power plant of 150 degrees Celsius. And the information here was based on former reference data, boreholes and reports, regional maps, 2D seismic data, and different analysis. And you see here the profile somehow. So we have a large Mesozoic sequence. Then we have, because it's located at a salt pillow, a very thick Zechstein salt section, and the reservoir itself, it is in the Permian Rotliegend. So in the Rotliegend section, the Detling formation, the depth of 4.2 kilometers. So however, at this site, we failed to install and to install a thermal loop. And the question was why? And there we decided and got money for a 3D seismic survey. And it was expensive, but it was financed because we want to know, we want to understand what's going on there, why it's not working. So there was several ideas that we have some compartments, that the internal reservoir structure hindered this, or that there even might be some free gas water contact. And we did different analysis on this and could show that we do not have any fault structures like they were interpreted based on 2D seismic before. So they were simply not there. So quite interesting. So what now? Yeah, and then we have also applied the DAS technology, so distributed acoustic sensing between boreholes, and got a very nice resolution between the boreholes. We have 2 boreholes there, and also showing that we do not have any compartments in that area. So we need to understand what's going on, and I like them to start and pick everything what was available from data before. So I used the new 3D seismic data to get some information about the horizons and the general structure. And then I go back to all the data we have. So there's a lot of former industrial data, which was not corrected for in situ conditions. We have a lot of logging data available, which was also not interpreted in terms of the reservoir properties. And we also did an assessment of the thermal properties of the wells. And very relevant, at that point, nobody discussed about the facies and so how it is composed, the internal structure of the main reservoir sandstone. Based on this, it was possible to set up a structure and facies simulation model for the site. And here within this yellow area, this is the main reservoir sandstone. And based on this facies distribution, we could then assign the petrophysical properties, which are shown here for the 3D volume of the project. And finally, this could then be used to evaluate once again the site. And the result of this is we have a very low porosity, we have low initial permeability, there's no compartmentalization in this region, but we have very saline waters, which causes a lot of problem, and this is also causing precipitation and scaling in the borehole. And we also realized that the stimulation which was performed at that well is not sustainable. And right now is under consideration of fracture-based EGS for the system or a multi-well exploitation concept. And also maybe using the upper Mesozoic reservoirs for heat provision. And this maybe we will discuss also later, because I do not want to go too much into timing issues. Because this also has something to do with how you support the geothermal industry to be on site. And, so for Germany, it was a long time just selling power generation and not heat provision. So finally, I would show you also another example for a project in Potsdam, which is very recently. This is quite interesting because it is also located in a city. It is designed for heat provision. And in a city always means that you are not so easy doing geophysics. You cannot do electric measurements and geoelectrics. You cannot easily do seismic data. You have to convince the people. Nevertheless, they did several 2D seismic lines before the drilling because they want to ensure that there's a successful project. And the target was determined to be some Triassic Buntsandstein sequence. And it was interpreted, and then the drilling starts and the fun begins. So with a lot of different on-site field laboratories and investigations, and then we realized, okay, something is different than expected, because the seismic data was indirect data. It was not foreseen that we have what is assumed from the preliminary profile, a reservoir section which is now more than 650 meters deeper, with a thickness of more than 70 meters, is now in a range of 1.7 kilometers. And that the targeted reservoir, which will be much deeper, where nobody had designed the drilling for something like this, so it was not possible to access it in any way. But the good news for this project, this reservoir is suitable for heat provision, and it's better than any Buntsandstein area, I'm pretty sure. So very lucky. So we see here seismic data is indirect information, so we always need a drilling to show what's going on. And this alien sandstone is a very good geothermal reservoir, and also now we have a doubling the expectation. So from the expectation, that's very nice for the company, and now we are starting to set us a heat provision for Potsdam. Yeah, so with this, I want to conclude with some more general comments. So, because I didn't focus in detail on the cross-scale interpretation, but I think this becomes very clearly from the work in the North German Basin, at least, a facies-based geological triggered way of doing it is more successful. And it's more easily to integrate all the different data you have because you have to put it into a geological concept. That's quite nice. And you need to do it iterative because you always get new data and they will not stop when you come into operation with something. So most important points are getting access to subsurface data. And I think this is really relevant. And you need boreholes. Without boreholes, you will never have direct access to the data. That's sure. Deep boreholes are helpful, especially for temperature profiles. And if you have known thermal properties, you can understand paleoclimatic effects, and you can also document ongoing climate change. You need to combine subsurface data and surface data, and this the type of application, because it also matters. Most often you just design something for heat provision using hydrothermal, but you need to train the engineers that they also think of what is possible, what the subsurface can deliver. So to keep it the other way around. And this is a process we realized because you need at least an option B or C if you start a project. Otherwise, you have a failure and that doesn't sell. So you need to have some ideas. So if you design something, think of if there is some, if it's a small benefit, something which you can make out of the project. And exploration is ongoing target as long as you do have a project in operation. So this will also help in future exploitation strategies. So thank you so much.
Thank you very much. So our next speaker is Ilmo Kukkonen from University of Helsinki. Thank you.
Ladies and gentlemen, dear colleagues here, it's my pleasure to be here and share some of the experience we've had in Finland in deep EGS development. First of all, why am I here talking about an industrial project? I'm a university professor, but I've been involved in this project since about 2014 when they started to look around for geoscience specialists because they didn't have anybody in the company, but they still had a project going to drill to 6-7 kilometers and to make an EGS heat exchanger there. So I came along and I had the pleasure of helping them in geoscience questions and deep drilling for geophysics and geothermics. Thank you. So, first of all, what I'm saying here are my opinions and views and not of those of the company. Now, the ST1 is an oil and gas selling company. They're also refining hydrocarbons. But they also, that's where they make their profit. They invest quite a lot in renewables like biofuel. They have companies for producing shallow heat exchanger systems, etc. And they also took this serious interest in deep EGS development then about roughly 10 years ago. And there was this project, the Deep Heat project, that was active about, sorry, that was not my intention. So, okay. The pointer is this one.
This right?
That is pointer.
Yeah. Oh, pointer is in the middle. Apologies.
Okay, so, okay, so thank you. Okay. Anyway, so this is a peculiar project in the sense that they started just like that to make a project aiming to drill to 5 to 6 kilometers, stimulate the boreholes and have a reservoir there. That was the idea, and then the purpose was to produce heat in the power plant next to the borehole site, providing district heating energy in the local network. The drill site is located a few kilometers from downtown Helsinki, which is here on this geological map. So it's here, it's a university campus. Geology represents hard rock, shield rocks, granites, gneisses, and phthalites. They're typically also steeply inclined, so no horizontal layering, and all the permeability is provided in the fracture and shear zone. So it's the fracture porosity which is important. Heat flow is normal, about 55 milliwatts meter square, and the project completed 3 boreholes to 2 kilometers on 1 fully cored borehole and 2 rotary holes, water hammer and air hammer and rotary holes down to 6 kilometers. And the deeper sections were deviated to find the optimal orientation in relation to the local stress field and the opening of the fractures. So, what I'm talking today is very shortly about the reservoir temperature and the structure, the stimulation and the hydraulic conductivity results, and the project status. Okay, we have the 3 boreholes. Their colors are very close to each other, within about 20 meters. So here is OTN1, 2 kilometer deep, fully cored borehole, and then these super deep boreholes, OTN2 and 3, that go to more than 6 kilometers driller's depth. So they're really super deep holes. What comes to the drilling, all 3 wells were successfully completed, and different technologies were used. The most efficient in terms of penetration rates was air hammering. It was possible to reach daily penetration depths of something like 50 meters at most with the air hammer. Water hammer was tested. It was never really economically functional, so it had to be abandoned. And finally, the deeper part, half of the holes were finished with classical, traditional rotary drilling. So in terms of drilling, important know-how was attained. Here's the temperature data. Now, we have here, this part represents an equilibrium log in the 2 kilometer deep borehole, and the green line below that is a model temperature. And all the other curves are logs obtained during different stages of the project. So they are disturbed by drilling, they're disturbed by stimulation and flow in the hole and whatever activities. You can see there's a drilling and a technological disturbance of about 10 degrees between the undisturbed and the disturbed temperatures. And we have various variations. But some of these curvatures here already in the first 2 kilometers represent actually directly this already discussed glaciation, paleoclimatic disturbance. Now, we see now from that the temperature at the depth of 6 kilometers is about 110 degrees. And the gradient is getting close to about 17 to 20 degrees per kilometer. And one important thing to take into account is that the fluid salinity is very high. It's up to 170 grams per liter, and they are chloride waters with sodium, calcium, magnesium, and other cations. And like what Ben said, it's indeed the same issue. What can you do with this kind of a fluid? It creates problems in concerning the casing corrosion. It may be a problem if you have to dispose that somewhere on the surface. That's a problem, and you should not play around with such a fluid. Okay, then some of the structural studies. It's an urban site. It's a university campus. You can't run extensive 3D seismic. You can't run Magnetotellurics there, and therefore they had to start drilling blindly. And but one important exercise was done with the VSP survey in these boreholes, and with the vertical seismic profiling, which is like turning the normal reflection seismic survey to a vertical position. It was possible to delineate a very difficult drilling terms, very difficult zone of fractured and sheared rock. That is also the part of the reservoir. So here in the VP velocity log, you can see this few 100 meter thick, very low velocity zone that is due to fracturing and shearing of the rocks. Okay, then the stimulations. Now, EGS system is based on the idea that you have 2 boreholes that have the lower ends have a distance of few hundred meters between each other, and you're pumping fluid down, cold fluid down in one hole. It flows through the formation, and you're pumping it up in the production. Now, for that, you need a good hydraulic permeability, good hydraulic conductivity in the formation between the wells. But usually the natural permeability is too low. You have to improve that, and one way to do that is to use hydraulic stimulation. Both deep wells were stimulated, and maximum overpressures up to 900 bars. That's a huge overpressure actually, was used. And you can see here, this is the pressure development in OTN3, and these stimulation stages represent about 100, 200 meter long sections in the deepest section of the well. And the flow rates of the ingoing fluid is something like 400, 800 liters per minute, quite a lot. And then a total of 1,800 cubic meters of fresh water was injected to the formation. That creates pressure there, changes the pore pressures in the fractures, and as a result of that, we get induced seismicity, and this induced seismicity was kept between the so-called traffic light limits by controlling the flow rates and the pumping pressures. So that went all well. So no serious seismic consequences were generated. Then, with the induced seismicity, you can define the spots and the places where the earthquakes happened. All these earthquakes were very small, so magnitude mostly below 1. And these events are very small. The slip in those fractures is less than a millimeter, but still they were felt on the surface and measured with instruments. And the stimulation created not one single kind of a swarm of spherical bubble of earthquakes or events. There are actually 4 of those, and they are quite complicatedly situated, and of course controlled by the geologists somehow. And we can discuss this in more detail, but let's go and look at some of the hydraulic conductivity results. So as I said, conductivity is the most important parameter in creating an EGS next to temperature. And here's an example where we have estimated the hydraulic conductivity during the increasing pressure phase and then the transient when the pressure is relieved. And you can see that during the injection, there are the blue bars, and the orange bars are the recovery data. Systematically, the injection hydraulic conductivity is higher than during the recovery. It means that we are opening the fractures that are there already in nature. They are opening, and when they get wider, the permeability increases. And this is the effect seen, but when the pressure is relaxed, the fractures close again. So the bedrock behaves elastically. And sometimes I call it, this is like playing an accordion. So you're pumping it open and close. And this is systematically seen in all these experiments. Here is a compilation of the hydraulic conductivity data showing that it's pressure dependent. Here we have the maximum pressure applied at the wellhead, and here is the net pressure, so the pressure above the level which opens the fractures. The leak of pressure test indicated that you need, at 6 kilometers, you need 52 megapascals, so 520 bars of pressure to open the fractures. And here they are open, but here they are less open. Now, when we do this kind of an experiment, we see that, okay, when you start the experiment, you quickly increase the permeability, conductivity, like this, apply more pressure, and you will get high values which are about 2 orders of magnitude than the natural values. But when you relax the pressure, it all returns back. So we have here shot-in data collected after a few months after the stimulations. So a lot of work was done, but it was difficult to keep the improved permeability because of this elastic response. But and it was not finally possible to generate the flow between the boreholes. So not a single molecule of water going down from one was pumped up from the second. But we observed a pressure effect between them, because when the OTN2 well was drilled to the end and its stimulation was started, so in about a week's time after that, in the wellhead pressures in the neighboring OTN3 well started to change, and they nicely then recorded the pressure signal from the formation. So this is diffusion of pressure, but it's not the flow of fluid. But there is a connection. But from this data, we can estimate that the average conductivity is about 5 to 10 to minus 10 meters a second, which is about average normal value without any stimulation activity. So the permeability is on the level of 10 to minus 70. If you compare the conductivity estimates in the results in the continental crust in general, this is the curve produced by Manning and Ingebrigtsen in a classical paper on this hydraulic conductivity and permeability of the crust. And you can see that the data we obtained at 6 kilometers in this ST1 project show that the stimulation time high pressure results are about a couple of magnitudes higher than the average, but the data during close in and shut in of the wells are returning back to the normal. And this is a kind of a important curve to take into account. So the deeper you go, you're planning an EGS, the more difficult it is to make the fluid flow, because the conductivity scale is logarithmic. You go down from the first kilometer level to 6 kilometers, and you have about 3-4 orders of magnitude drop in the hydraulic conductivity. Means that your flow rates are also decreased by 4-3 orders. This is dramatic. It's a major engineering barrier in starting to create EGS systems at great depth. So I would say the temperature is not difficult to reach with modern drilling technology. You can reach 100 degrees or so, no problem. But make the water to flow there is a real challenge. And we then, excuse me, look at what kind of a thermal power can we reach from the system. So we can use relatively simple models. This is based on the Moyes equation. You can find it in every hydrogeology textbook, and it correlates the rate you pump into a borehole section and the applied pumping pressure. And now the flow rate you can reach depends on the permeability, which is here on the as a parameter of the curves. And they were planning to use pressures about 300 bars or even higher. And if the permeability were about 10 to minus 9 meters per second, as it was due from the stimulation experiments in the high pressure range, it would have been possible to pump in about 100 liters per minute. So this dashed line here. So that would be the level. So what would that mean? It would mean, if you calculate the pump rate, simply calculate what is the heat content of such a fluid when you take in 100-degree temperature and you return it back at 50 degrees. That would be the normal system in a district heating system in Finland. So your 100 liters per minute would indicate a thermal power of much less than 1 megawatt. And I'm sorry, this is peanuts. The original goal was to make 20 or even 40 megawatts thermal power. But that would require a much higher, even exceptionally high numbers of flow rates, because you see the curve flattens out here, and it would require extremely high values, which are not reasonable anymore. So this sort of lessons were learned. The drilling is successful. That's easy. That just requires money and engineers and drillers. The temperature is very nicely estimated. The error is not too difficult. If you have 1-2 kilometer pilot holes that you have locked the temperatures in equilibrium conditions, you can make very reliable models. But the hydraulic conductivity, this is the most challenging part. We had this high pressure conductivity increasing to this 10 to minus 90 meters per second level, but the natural level is about 2-3 orders of magnitude smaller. And that is something very difficult to change. So the stimulation did not permanently improve conductivity due to this elastic response of rock. Now, oil and gas industry uses often proppants, mean that you are pumping with the water and the fluid, you're pumping in sand, like or ceramic particles that will carry the fracture walls when the pressure has been relaxed. But this is very difficult to use, and in these conditions, with these very high pressures of lithostatic pressure 6 kilometers, the result would have been that we would just crush the proppants, and or the ceramics would have been squeezed into the rock. Even that would have even decreased the permeability. So, for these reasons, the EGS construction and the project were as such, it was terminated. But what then? We have 2 super deep boreholes. They are open, they are accessible. You can drive with a car next to that. Metro station is 200 meters away. And we have a development going on that we want to develop this site to kind of a borehole observatory. And we have an ICDP application, a workshop application was accepted earlier this year. Next year, there will be an international open walk workshop. Everybody is welcome. Somebody will be supported, but not all. But we are inviting at least a few tens of people to discuss what kind of a project could it be and be prepared for the final application. And this deep EGS is meant to extract all the possible information from the experiments done already at the ST1 site, but also to make new ones as far as possible. And already 2 weeks ago, we were able to carry out logging and sampling campaign on the site. We logged temperatures down to 4.6 kilometers, the deepest ever equilibrium temperature logs in Finland. Very good results so far. They look very interesting. We have also very interesting observations of free gas in this section there. And we did fluid sampling for geochemistry, isotopes, also the residence times of water, and also for microbiology. Because in drilling trials already, samples were taken and it was noted we have the deep biosphere at about 4 kilometer level where those samples came from. So extremely interesting thing, industrially not perfect success, but a lot of was learned, and a very bright future perhaps for a borehole observatory project. You can find a number of papers describing mostly the seismic studies, but also the hydraulic conductivity estimation and these things. So with these words, thank you very much.
Our speaker is Michel McKenzie from the Department of Economy, Northern Ireland. Thank you.
Thank you very much. Hi, everyone. Yes, my name is Michel McKenzie. I work at the Department for the Economy. So the department is one of the devolved government departments in Northern Ireland, which has a wide remit of which energy sits in. And the department is delivering this project, GeoEnergy NI, which I will talk about today. So the department, how we got to the project, I think this is a very, very quick snapshot because a lot of work went into getting it to the point of delivery even before the energy strategy. A lot of hard work by officials in the department, the Geological Survey and Queen's University Belfast. But for the first time ever, geothermal featured in the department's energy strategy, which was released in December 2021, which set out the pathway to 2030 that will enable success to net zero carbon energy by 2050. And subsequent to the energy strategy, annually, energy strategy action plans get released. And in the first energy strategy action plan, there was a commitment to undertake shallow and deep geothermal feasibility studies, which is what we're doing. And that's GeoEnergy NI. So an overview of the project aims is really to showcase and demystify geothermal, better understand subsurface, encourage and de-risk private investment, and quite crucially, gain public support and social acceptance for geothermal in Northern Ireland, as well as using insights from the project and findings to better inform a development of a policy and regulatory framework in the future. So a lot of the project centres around the Sherwood Sandstone Aquifer, which been mentioned a lot today. So it is fairly prominent across Northern Ireland. It appears at shallow depths underneath Belfast and then deepens out to the west. And that's informed the design of the two studies that we're undertaking. So underneath Antrim, it sits at about 1 kilometre depth to the top of the Sherwood Sandstone, and typical temperatures I expect sitting at around 40-45 degrees Celsius. And then obviously shallow underneath Belfast, maybe at the 200 metre mark. So at Stormont, where we're doing our shallow study. So Stormont Estate was chosen. It is the seat of our local government. This was seen as quite an important location to show government confidence in geothermal as a technology and to be a very prominent and visible place to do this demonstrator. So the shallow study is a drilling program of 5 boreholes across the Stormont Estate. So 4 hydro boreholes up to a maximum depth of 250 metres, and then 1 stratigraphic borehole, which we took core out of. And a lot of work was done in building up the geological model beforehand. And then we have the drilling phase that we're currently in. And following the drilling phase, we're going into the testing phase, that will test various parameters to understand whether open loop potential or closed loop potential would be most suitable for some of the buildings on the estate. And the idea would be to inform the design of a suitable system to help decarbonise some of the buildings across the estate, including some very iconic buildings, including our Parliament, Stormont Castle, etc. So this is a site plan of our projects on the Stormont Estate. So you can see the 5 boreholes dotted across. And so there's the stratigraphic one in the south with our first hydro one there. And so the idea was to try and capture data across a wide area as possible, with consideration to the sensitive receptors that are across the estate. So we have protected species, we have listed buildings, all need to be considered when we're designing our drilling program. So we completed our stratigraphic borehole, and we completed it at 303 metres once we entered and confirmed salary grey rockies that were of less interest to us. So we decided to cap it off there. The results from the stratigraphic borehole have helped to inform the approach and design for, well, it's design especially for the remaining boreholes, and then the approach for the testing program, because we're testing different parameters in different boreholes. So just to understand better what would be most suitable, what could we get the best data out of, what would be most effective with the resources that we have. So the core that was extracted out of the stratigraphic borehole has been transferred to the core store, JSON ions for further analysis, including works that Rolf has started with the scanning electron microscope. The drilling program is due to complete in end of November time, and we are due to receive the results around January time, preliminary results and reporting from there. Moving on to the second of our feasibility studies is the deep study in Antrim. So Antrim has been talked about a fair bit today. We undertook a series of geophysics surveys around the Caffrey Greenmount site, which is owned by another government department, the Department for Agriculture, Environment and Rural Affairs. And it was a perfect partner for us to use the site as a base for our surveys and then survey around the site to understand the geothermal potential underneath in better detail. So I undertook a seismic reflection survey, gathering 15.4 kilometers of data along 3 2D lines. We had 100 gravity survey stations deployed and 19 MT stations. And the 2023 data was complemented by a good amount of legacy data, including MT from 2009, lots of gravity stations, historic seismic lines, and we did have the historic logs from proximal deep boreholes that we were able to use to interpolate and confirm what we were seeing in some of the geophysics. So just to highlight, been talked about a fair amount today, that there are basalts and lavas in Antrim that I guess do present challenges when you're going for when you're trying to image into the subsurface. But they also contribute to the opportunity of the elevated geothermal gradient and the potential of the area for using that heat. So that red box there, it's slightly smaller, I think, than what our survey site was, but that's the rough area. And there's the cross-section along the profile to the northeast of our survey site that just highlights some of the big structures that are occurring, such as the 6 Mile water fault that kind of bounds into the south of our survey area, and the Brown's-Out fault to the northwest. As I said, we had lots of historic data that we could use to help confirm and inform our understanding, complements the newly acquired data from last year to help build our 3D model. So this was one of the seismic lines on the other side of the loch, Loch Ness. And this is a combination of the MT that was gathered with the seismic, and you can see just here, this anomaly is the pick of the Sherwood sandstone. So lots and lots of good data across the wider area that's really helping to inform some of the big complicated structures and best inform what the design of a system could look like. We've talked a bit about money, and you do want to be suitably prepared before you start to hitting the ground, because it costs a fair bit of money, and you want to make sure if you get it right as best as possible. So some of the preliminary results, this is some of the early MT that we gathered. So this is a profile extending down here. These blue triangles date from the 2009 survey of MT, seen up here. And then the red triangles are the new data acquired in the 2023 surveys, down here. And then we have the Ballymacroy borehole just here in the northwest. And we can see lots of commonality between the two, and we can see this lovely resistivity anomaly here that we're able to use the existing data and interpolate from the existing Ballymacilroy log to identify and interpret the Sherwood sandstone. So we also have a very clear and crisp image, which I think speaks to the quality of the MT that we gathered, that we are very chuffed with. I think it's very good quality data that we've gathered. And so this will feed into the wider 3D model that combines and inverts the seismic, the gravity, and the MT to build up this 3D model. It is currently in the process of being finalized. I was quite keen to be able to show a bit more today, but you'll just have to wait. Hold on to your hats. We have also, we like research in our team. And so we commissioned some research into understanding what the potential operation could look like of a deep system targeting that Sherwood sandstone aquifer on the Caffrey site. So we commissioned research that did numerical modeling of various different types of geothermal systems, whether that was open loop doublets or closed loop coaxial systems at different depths, just to understand how that system could perform over an extended period, what temperatures we'd be looking at, the thermal power, the yield, the various parameters that we could hope to expect from that system. So for a 1 kilometer open loop doublet, we see typically temperatures achieved of around 45 degrees Celsius, and there is some slight thermal breakthrough at 100 meter separation here between your abstraction and injection. So 200 meter separation design would be probably preferable, get minimal breakthrough. You could expect to reasonably abstract 20 degrees Celsius, have a delta T of 20 degrees Celsius, and pump at about 20 or 30 liters per second. There's some slight breakthrough there, but not so significant. We also got modeled, and for comparison, this is what the same kind of modeling looks like at 2 kilometers at the same site. And even though you are targeting higher temperatures, 70, 75, because of a poor quality of the reservoir, you start to see some pretty severe thermal breakthrough and loss of efficiency in that system. So that's been an important one to highlight to project partners, that deeper isn't necessarily always better. It's a bit more nuanced than that, but you can still enjoy some very fantastic benefits at shallower, say at 1 kilometer. As part of that research, we were also delivered some economic analysis and some estimates of thermal power. And this is where folks in government's ears usually perk up a wee bit. So this is a table summarizing the thermal power of the various types and settings, whether that's an open loop doublet at 1 or 2 kilometers or a closed loop coaxial. Expecting possibly a thermal power in a 1 kilometer open loop doublet on the Caffrey site of 2.5 megawatts. At 2 kilometers, it could be 1.6. A big variation in coefficients of performances of that system. But the really key thing and quite exciting thing is the levelized cost of heat that could be on offer for a functioning system in these settings, like 3.7 pence per kilowatt hour, a fraction of what gas is at the moment. So I think that helps to take this thing out of the capital costs when we're talking to people, when they see the efficiencies and the running costs and the potential in the longer term. Looking at communications, so the GeoEnergy NI project, as well as being feasibility studies, a big thing is demonstration. We know that a big barrier to geothermal uptake is lack of public awareness and lack of engagement. So as part of the works, we have a communication strategy that's undertaking various activities to boost awareness of geothermal in Northern Ireland and potential that it offers us. So we kicked off with pre-campaign surveys to understand what the baseline levels of awareness were of geothermal in Northern Ireland. And we're following up with a post-campaign survey in early 2025 to measure, hopefully, some impacts in our work. Hopefully see shifting of the dial somewhat. We do a fair bit of media collaboration, working with a range of media types, whether it's TV, radio, print, for different purposes, different stages of the project. We have also delivered an interactive mobile visitor centre called the GeoEnergy Discovery Centre, pictured here in the background, which features our designed VR and AR programs, which help to image down. We've designed a 90-minute program covering aspects of energy, renewables, geology, geothermal, everything you'd want. And so one of the favourite parts of the program is you go down underground in a replication of the geology underneath Stormont, and you get to see how things were deposited and what it's made up of. I think that helps people relate and bring it to life a bit more. So we do lots of public engagement with that as well. And we do a fair amount of educational outreach. So at the moment, the Discovery Centre is going out to schools across Northern Ireland weekly for set days where schools will come and visit and spend 40 minutes learning about the various aspects within the centre and some of the key messaging that we want to get across. GeoEnergy NI have worked on and delivered a set of teaching resources for Key Stage 2 pupils, and are currently working on a set of Key Stage 3 resources. Also, important to provide as much support as possible to teachers to try and factor in geothermal and increase the messaging wherever we can, and help to pitch it to different audiences. And we do have our project website and our social media. There's our handle there. The project website has updates from the project on kind of major milestones, all the information you'd want from the project, lots of case studies of installations, everything you'd want and more. So it's all part of a very kind of intentional effort, understanding that awareness and acceptance of geothermal as an innovative renewable technology is key to expanding the market, generating interest, generating private sector interest, and encouraging uptake. So to summarize, GeoEnergy NI is the public demonstrator project exploring shallow deep geothermal feasibility. We are making strokes. I mean, we featured in the current programme for government, which is a huge achievement for us, and I think that speaks to some of the work that we've done in raising the profile and awareness of geothermal. So that was released last week. The shallow feasibility study is underway, with results expected in early 2025. The deep study the results are currently being finalised. The results of that will be used to inform the siting of a potential deep borehole system. So something that I wasn't sure if I'd have time to talk about today, but we also consider the planning system as almost a test of feasibility. So we have undertaken at the Caffrey site a years-long environmental monitoring period in preparation for submission of a planning application for a deep system, and that planning application will be submitted before the end of the year, or at least start to get submitted, so that we can understand the process, what's required, what data is required, to enable a functioning deep geothermal system, especially in an area of special scientific interest, where there is a higher threshold, and there will be scrutiny on it. So results from both of the studies will inform decision making of potential future phases and inform a future policy regime in Northern Ireland. We have learned a lot in the projects, and it's been very illuminating. So I think it has helped to equip us to understand what needs to happen, in some senses, in a policy regime. Data and findings, I think as mentioned earlier, will be open access when we are ready to publish them. That's a really key thing, really key principle for us, making it all open access for future use for anyone to use and play about with. And yeah, follow our channels because lots of stuff is going to be coming out in the next 6 months, and it's going to be quite hectic, but it should be quite fun. So there's a link to our website, and yeah, it was.
So our next speaker is John Walsh from UCD, and he's going to talk about the GeoEnergy project. Thank you.
4 o'clock, Aoife. I was already getting the look. So this project is from UCD campus, and the basis of it is that we're trying to prepare the ground for actually having a geothermal system within the university. There's a cast of thousands here, and they're mainly from UCD, from the UCD Earth Institute, from ICRAG, from DIAS, and from various companies, Venterra and Cosmic. So, how do I do? Do I do it this way?
Yeah,
I can do it.
No, not that one. The right arrow here.
Oh, very good. Thanks. Yeah, there we go. So the idea is that UCD has a district heating system, and there's lots of different sources, potentially at least going into that district heating system. There is mainly, though, it's mainly gas boilers. There is some biomass, not much solar, CHP. There's also air source heat pumps now more recently. The idea is that to explore with this project is to explore actually including geothermal as part of the sort of heat mix, and to increase the renewable usage in UCD. The project, the GeoEnergy project, has 3 main work packages. I'm mainly going to deal with work package 1 and 2, but each of the 3 is important and complementary. So here's the 3 work packages. 1 is 3D modeling. Work package 2 is thermal modeling, different types of thermal modeling. And work package 3 is looking at sort of techno-economics and trying to arrive at the optimal mix of different types of renewable heat sources. Here's UCD. Here it's on the hanging wall, the down-thrown block of a major carboniferous normal fault, which is about 2 kilometers displacement. So we're in a good place there. In fact, there's a splay, which we think goes on to the Holt fault, which actually bisects UCD. I'm going to deal with work package 3 first, and I get it done and dusted. But we've looked at the heat demand and heat usage on the UCD campus over the last 6 years. So each building, at each period in time, we can chart exactly what heat has been used within the campus. We can, as it happens, it straddles COVID period, which is totally unrepresentative, but we actually have periods from before COVID and after COVID. And these are the sorts of heat loads which they place on. Some buildings are more than about 500 kilowatts. Some of them are even larger. This one here, the one that I actually have my office in, Science East, is about 1.5 megawatts. So if we can contribute something like 1.5 megawatts, that's a significant part of the UCD's sort of usage. It's probably about 20%. But different buildings, some of them are on the district heating system and some of them aren't on the district heating system. So for those, for example, if you could get a geothermal source, you're immediately switching off gas pumps and saving CO2 emissions. This is a heat map just to give you an idea. So these data, annual and seasonal data have been looked at by the Energy Institute, the UCD Energy Institute, in terms of heat sources, the costs, isolation or links to the district heating system, and so on. These are all part of, they basically define as to what is the best way to do this and whether in some cases it's not worth pursuing. This is just showing them through time here. Yeah. So I'm going to leave that behind. I'm going to get into the geology. And this is work package 1. This is why UCD is important or interesting from a geothermal perspective. Here's this major fault, the Blackrock Newcastle fault, about 2 kilometre displacement. And here's the splay, and here's the UCD campus. I'm going to walk you through a few of these points here. We've looked at the stratigraphy. Kuhn, Tormans and others have looked through the data on borehole, deep borehole data. Here's a sort of fence diagram. It shows the Blackrock Newcastle fault. This is the north side, and you can see that there's these grey rots here. These are the Lucan Formation. The blue are Walsartian, the slightly different blue is Allenwood, and so on. So we know the sorts of formations that exist in this area and are likely to exist in UCD. And UCD, there's Grange Gome, and UCD is in a position around here. So we know the sorts of formations. We can take, and Pablo has done all this work. Pablo is in the back. He's just arrived there about 10 minutes ago. He worked, generated this sort of divided bar apparatus, and he's been measuring thermal conductivities for things like the Lucan Formation, the Allenwood Formation, the Walsartian Formation, the Ballysteen, all of the formations we need, doing it at different, whether they're saturated, dry, or just take them as we've got them. It also measures the system that he has, densities up here, and also porosities. You can see the Lucan is very tight, but you can see that the Walsartian has a bit of porosity. It's a lot of porosity. The Ballysteen and these samples here, a little bit more porosity. So these different sequences offer different opportunities. We're looking at geophysical data. Duygu has looked into the possibility of doing passive seismic here, but we don't have the right circumstances. We'd like a railway going straight through UCD, and for some reason they won't agree to it. So instead we've gone for gravity data, and Duygu and Dimitri have done gravity modelling, and we've ended up with, this is an interpretation from seismic data about 10 kilometres to the west there, and it's a terraced fault system, this main fault, dipping to the north and down throwing to the north. And this is what their gravity modelling shows. This is the main Blackrock Newcastle fault with granites here on the south side, carboniferous on the faulted, multiple faults. And these gravity lows here we think might be karst, or might be karstification of fault surfaces. So we get a sense of what the structure is. We can pull them into a 3D model here, and this is the main Blackrock Newcastle fault. This is the main splay. This is the Holt fault, and we're getting a 3D sort of model coming through. We got resistivity data, which we got from Minerex. They'd done a job for UCD several years ago and back to 2008. And those data, they give us a sense, without getting into details, they give us a sense that there are these structures, the ones that Hunstown is on, where you've got warm springs, they may be extending into UCD along these northwesterly trends. Do you remember the things we were talking about, these possibly tertiary northwesterly things? So UCD is in the eye of a faulty storm, which is excellent, because I'm somebody who's very faulty. And these faults are important because they give you porosity and permeability potentially. Here's Hunstown, and you probably can't see it, but there is actually water coming out of this structure here. These strike slip faults, Cainozoic, they have the water bearing, and we think they could be some of the most important structures for giving us flow in the subsurface. Here, if we're in the sort of more mudstone-rich sequences, we get different spacings compared to if we were in the likes of the Walsh Ocean. And that's important. So we can use constraining data on fault density for different rock types, massive limestones, tin-bedded limestones, as part of our parameterization for property modeling, for example. Getting into the boreholes, I'm not going to bore you, but here in blue are just all limestones. Here's the Holt Fault, and these are just different sites with limestones. There are actually granites in the near subsurface in UCD. There's granite obviously much further south below the main fault, but there's actually granite very close to surface in UCD, which we didn't expect. And here we've got borehole data, which shows this sort of red granites and so on here. And another big chunk. So about 30 meters below the surface, there's a big granite in UCD. Yeah. And further to the north, this is the main Holt Splay. We get limestones, and these are limestones, interpreted limestones. The dark blue are slightly karstified ones. We got multiple holes. And this, just see that yellow box? That's a hectare which UCD estates have identified as potentially a place we would put a shallow geothermal array here. And that shallow geothermal array is right beside the energy centre in UCD. And I'll come back to that in a second. Here's our 3D model. Here's the main fault with the red granites in the background. Then there's granite in the near subsurface here. Here's our splay coming off to the Holt Fault. Here's the stratigraphy of the cover sequence here, which are limestones with the different horizons, the Ballysteen, the Calp, which is the Lucan Formation, and so on. And this is a 3D model, which is all very vulgar. And oh, here we go. We're going to rotate in 3D and get a bit squeezy, creasy. Are we doing? We're doing okay. Yeah. So here's the boreholes here. Oh, sorry, I pressed the button wrong. It doesn't matter. Here's a 3D picture here, and it's actually showing the heat in place. So we're using the sort of data which is underpinned by the likes of the work of Dias, for example, and we're using certain heat flows at depths, and those at 2 kilometers depth, we've got a sense of what the temperatures are, but we can now take our 3D models with the properties, the conductivities, and we can basically work out heat in place up to the surface. Yeah. And you can probably see the fault. You may not be able to see the fault. It looks a hell of a lot better on this screen. Oh, is it a lot better here? Oh, God, it's a lot better here. Good. So you can actually see the faults and so on. So, and we'll combine that with data. I'm not going to get into it, but looking at data for the spacings of fractures, because these are a critical determinant on properties, the spacings of fractures and the apertures of fractures. So we have data from outcrop studies looking at things like that, and from that we can get sort of porosities and permeabilities, which are fracture related. We can also tie in with transmissivity changes with depth, which are important in the shallow subsurface. So the question is, I've only got a few more slides now, but we had originally just thought that what we do is a deep geothermal project. But we don't have seismic data, and we don't have a borehole going down to 2 kilometers. So that seems self-defeating, if not stupid. Stupid, probably. So instead, what we thought, and because there are now an increasing number of projects which have been successful in implementing shallow geothermal, with UCD, we've been thinking in terms of shallow, deep geothermal scheme, which from other studies that we've looked at and combined, we think a hectare with 100 holes down to about 150 meters will give us about 1.25 megawatts, something like that, at a cost of 2 million. That sort of cost is perfectly fine. Compared to air source, UCD have just spent 1.4 million on air source, and it's a very inefficient way of generating heat. So this is a much better way to do it. And we're talking now to UCD about doing it. Some of the modelling I've mentioned. Some of the modelling that's been done that's going to be done is by Buddy and Shushu is here, and they're going to be doing the equivalent of fee flow modelling, which is doing thermal hydraulic modelling for closed loop borehole systems, and also for these standing column water borehole systems where there is exchange. So we're going to take sort of 100 by 100 by 100 blocks, and we're going to put in different layers, different types of limestones, different fault patterns and fracture patterns and porosities and permeabilities, and looking at sensitivity to those different parameters. And so they're conditioned on our outcrop measurements, but we think we can explore parameter space. And this is going to be using open GeoSys, which is the sort of open equivalent to fee flow, which is probably one of the leading thermal hydraulic modeling systems. Going to look at sensitivities and then try and get a sense of what the design and optimization for these systems. Should we really be doing 100 holes down to 100 meters? Or should we be doing 50 holes down to 200 meters? Because that might be a more efficient way of getting the heat out. And that might vary with fractures and so on. And so there we have an initiative which Cara English is heading up, which is we're working with UCD Estates to try. They've identified a patch of ground which we could potentially put a shallow geothermal. So we're putting together a proposal where we'll do a number of test holes, 3 or 4, as a prelude to having a tender for having shallow geothermal implemented in UCD. And estates don't think of it just as being one. They think of it potentially that actually UCD, oddly enough, it has quite a lot of land. Everybody thought we were rattling around in 40 years ago in a campus which is off town, but in fact it's a boon when you've got lots of land to put patches of these things on. And I've just put that in because it's an animation and it's in colour. But, and Buddy gave it to me. So that's the end. You get a sense. We're trying to square this circle here. So we'll be providing input in terms of geological terms to the flow modelling. That flow modelling will give us a sense of what sorts of energy we can generate, and our people who are working on the techno-economic aspects are already and have already modelled a lot of the implications of these and whether we can put in different point sources. That's me.
Our next speaker is Rory Dunphy, who is going to talk about the National Geothermal Database and defining data infrastructure. Thank you very much. You're here, right arrows, like the port, and the middle is the port.
I've completely run out of energy, so this will either take a long time or a very short time. It's short, but history would say long. So the National Geothermal Data Project, some of you will be very familiar with it. The purpose of it is it's a GSI project to collect and collate high quality data and make it publicly available to encourage basically sustainable geothermal development and inform policy, which is getting developed at the moment. There's 2 priorities. One is the short term, which is we very, very much we can complain about the lack of data we have, but we have to use everything we have to begin with. And so a lot of the work, and Vincent's going to be talking after, it would be one of the examples of where we're using what we have. This talk is actually more about the other part of this, which is the long-term thing, is that we know we lack a lot of data. What we want to do is develop programs for deep drilling, seismic and petrophysical to fill those gaps. The approach is, as I was kind of alluded to a little in some earlier talks, with geothermal, it's not oil and gas, it's not mining, it's very much driven by end use, and partnership is really important to us. We don't let the geology dictate where we go. We really look at who needs energy and can the geology provide what they want. And what we need to understand with that is a variety of different factors there. Geology is just one of those factors. It's only one of four that we need to understand. The critical thing as well with geothermal is geothermal really is geology and technology, and actually usually add end use as well on the end of that equation. There's more than one way to get the heat out of the ground. One thing we do know is that if you go down in the earth, it's going to get hotter. The heat is there. This is really an economic exercise. When we talk about exploration for geothermal in a low enthalpy environment like we're in, what you're actually exploring for is what technology will work to economically deliver temperature for the load you need and at the temperature you need. And because that varies. If you're after district heating, well, then maybe you need 50, 60 degrees. But if you're just trying to heat a greenhouse, you can have direct use geothermal that's much, much lower. You also, of course, have the option of bolting things onto different systems, because on the left, what you see is, the sort of think what's going to be the workhorse of geothermal in Ireland, which is ground source heat pump systems. They can come in a variety of different flavors, open loop, closed loop, but that's a well-established technology. At the right was talk of the Ever system, sort of the deep closed loop system, one way of doing the deep closed loop system, but there's others. And in between, we have what a lot of people would traditionally think of, and what we see today in terms of geothermal, which is, open loop hydrothermal doublets, where you produce from a reservoir and re-inject. Horace with that very interesting talk on Helsinki engineered geothermal systems, which even themselves come in some different flavors, where you're trying to create your own pathways and your own fluid movement through the rock. We in Ireland are not blessed with amazing geology when it comes to some of the deep open loop stuff. We're really going to focus a lot on these things, but we do need to establish if there is potential there. EGS, I think, in Ireland is probably a long way out. We have to rule out the other technologies before we get there, just by dint of the nature of the environment that we're in. When it comes to what the GSI is trying to do with respect to advancing all of those different technologies, it's important to recognize that they're at different stages. What we're doing here is creating a framework for interpretation and a framework for data infrastructure investment that's really about, at a country level, maturing your geothermal supply. This is heat is a country level problem in Ireland. It's 28% of our emissions. And so, we really need to think at a large scale about this. Our approach essentially is to start at the national scale, basin scale, technical work, the basics. What type of geology do we have? What type of systems might work? Quantifying that resource and moving, essentially funneling to the right here to get to the point where we can actually have demonstration projects, pilots, things like that. Now, when it comes to different technologies, 2030 is a big marker in Ireland in terms of decarbonisation. We're very unlikely to have certainly more than one deep open loop project by 2030. What we want to try and do is actually get to this point by 2030, where we've done a lot of the basin level screening and the prospect identification and maybe some piloting, exploration drilling, and we know what the opportunity is, and then you can get after it from 2030 to 2050. Whereas closed loop stuff, you can get after that right now. It's simply a matter of just making people realize it is not rocket science. It just needs to be designed properly, it needs to be done properly, but it's essentially ready to go. And the goal at the end of the day with all of this is helping people make decisions, which comes down to your euro per megawatt term or megawatt hour, and how much CO2 you're going to produce. That's what a decision maker wants to know, those two things. So all of our geoscience work is aimed at getting over there. The Geothermal Database Project, the PDP is the product delivery phase. It's really structured around sort of filling those different boxes on that last slide. So making sure we're not just focusing on piloting or not just focusing on regional studies, but covering everything. And so what I'll be talking about today is really sort of seismic and petrophysical stuff, but there's a lot on here. I think, one of the things when this project wraps up next year, I think we're going to do a workshop like this because I think it's a good format and actually cover all of this stuff in a lot more detail. Today, I really want to just talk about the sort of data strategy or data investment strategy piece. And so in work package 2, which is really all about that regional level, national level stuff, there's a number of different spokes that we have in that. In 2.1, it's really about seismic data, collating what we have, and defining, what it is we need to acquire. When you look at geothermal, especially open loop geothermal, there's really two things you care about: heat and permeability. And so when it comes to permeability, we're looking at fault systems in Ireland, karst, things like that. Very difficult to identify unless you have good seismic. And so that's why a strategy for data acquisition is important for seismic. When it comes to the heat side of stuff, as we've seen earlier, stuff like thermal conductivity is critical. It helps us understand the temperature gradient distribution in there. And when you get into closed loop stuff, it's absolutely critical because it determines how much heat you get out of a closed loop wellbore. So I'm going to use those two examples as to how we're thinking about sort of the long-term data acquisition strategy. So in terms of seismic data acquisition, I'm, I guess, an industry person. I always start with why, and my next question is always how much. And so this is really the critical thing with this, is to sort of say, well, we want data. Well, why do you want it? So it's seismic. In this is a report we've written for the GSI. It's really important role in geothermal screening, and the way to define that is to look at risk factors. There isn't a singular risking system for geothermal in the world like there is for oil and gas. So we basically built one based off a lot of discussions that we've had in other parts, other spokes of the project around fault permeability, things like that. And once you have a risking system, you can look at how would my perception of that risk, or how would the risk change once I have seismic data. And once you have that impact, you can then run economics. And so we looked at a deep case and looked at what would the economics look like if you were drilling blind, asking someone to make a decision, and what it would look like assuming you get seismic, assuming it's good quality seismic, and assuming that you can draw a conclusion from it. And in all cases, whether it's 2D seismic or 3D seismic, this should make perfect sense. There's a material outcome, i.e. the cost of the seismic that you require, the value that the NPV you get, the expected NPV from the project, in all cases was far superior to the actual cost of the data, which is a value of information exercise, which tells you you need to do this. But it's the key thing here as well is actually linking it back to what we're trying to do with the country level scale. Ireland has a strong push for district heating. We've never really had, like Europe, the large scale district heating. And so the SEI has defined 58 places in Ireland where they think the heat demand is suitable for district heating to put pipes in the ground. So what we've done is, you can't see it very well, but it's the sort of blue book provinces from the work that was previously done on the carboniferous in Ireland, and the red is the existing seismic data. And generally, the heart of the carboniferous is around here. There's not a lot of seismic data. So a lot of these towns fall in areas where we don't really have a good handle on the subsurface. We've improved it a lot with the modelling that Vincent and Pablo have done recently. But what we did basically then was rank those different locations as to, does it look like there might be a geothermal type play there? And then, what is in a given area, how many of these candidates are in there? And so those obviously would rank higher. So based on that, we devised different multi-year seismic programs and costed them. So you actually have an investment. Now, in between all of that, why and how much is a lot of work by Dr. Mark Muller on, we can't just put a number out there and say this is what seismic costs. The unit cost is somewhere between 6.5 to 30,000 euro per kilometre, because these encompass many different areas, of everything from rural areas to suburban areas to the street outside of here. And how you operate that seismic, how you design the seismic will change with the environment, the cost change. So we laid out the methodology, all the things to think about. You got to think of how wide you need to shoot the seismic in order to image the depth that you want. The rocks, they dip, will change that. There's a lot of information in there. And ultimately what we came up with is specs for each of those type of things. so that you can know, and any operator coming into Ireland will have a place to start to go, oh, you know, this is what we need to do. We want to get some seismic. They'll have a jumping off point to factor into stuff like economics. The petrophysical data strategy. So the seismic data strategy is all about what's new. You know, we really don't have very much. The petrophysical data strategy for the likes of thermal conductivity is all about, we don't have a lot of wells in Ireland, well logs in Ireland, because we never had a deep oil and gas industry. However, we have a mining industry, and we have a lot of core, and we take more of it all the time. And so what we have developed here is sort of an idea that what we need to be doing is creating core-derived log suites. Turn all of that core into actual geophysical logs that can be used to, we can use the seismic to define the frameworks, the different units. We need to populate those frameworks with, as you'll see from some of the geonorm stuff and from Pablo's poster downstairs, with the petrophysical properties that you can actually model and use to generate stuff like heat in place or recovery in a closed loop system. And so the idea here is that lots of people already doing lots of really good work on this type of stuff in Ireland, like Eleni Mello's group in UCD, DCD have a petrology lab. What we want to do is kind of have an overarching strategy where, you know, we can have workshops where we can develop multi-year plans, where we can have some layers of governance in there to really think about how we generate data, what equipment we have, what equipment we need, where's the money going to come from to pay for the equipment, and for that then to come down and how you're going to process data, how you're going to manage the data, where's it going to be stored. And this is all stuff that, you know, when we think of data acquisition, we think, oh, yeah, I spent X to get what, you know, Y amount of data. You need a whole load of people to actually manage the data, make it useful and get it out there. And so that has to be part of any strategy. And so we're obviously focused on the geothermal side, the geothermal database, but obviously this data could be used for mining, it could be used for hydrogen, it could be used for whatever you like. Within the sort of geothermal workflow, what we would be looking at is basically having a centralized lab where core could run through a process of getting scanned for different properties like spectral gamma ray, density, resistivity, thermal conductivity obviously being a key one, and then turned into, you know, core-derived log suites that then you can do your AI, your clustering models on, with geochemical phases, mechanical phases. We'll also have lithological phases where those descriptions. All of that stuff can be used to identify particular areas where you need, let's say, research. So I think the idea of having a national petrophysical lab is that you should also have a national research petrophysical lab to take on some of the more tricky and specialized stuff like geomechanics, which again, there's some folks in UCD doing. And the idea with that is to integrate this stuff. This is all centimeter scale measurements. It's all, you know, core stuff is at a low level, but from the work that you're going to see after this, where we're doing basin level modeling and regional surface interpretation, you have the framework there once you build the facilities to actually populate this out over the whole area where you have your 3D model. And so that's when you can do things like take your basal heat flow into a sedimentary basin and get your temperature gradient from it. So that's the key with that. With any of this stuff where you have data, you have to be able to move it one level up to show stakeholders its value. And so in work package 3, and this is what some of the stuff that Vincent will show, it's all about things like resource in place. Ashling here from GeoServe has been working on the shallow resource maps. And you can't see it particularly here, but these are things that people can go to and have information like, well, you know, in this particular area, there's a 60% chance that an open loop system might meet, let's say, a residential need. With the deep closed loop map, this is just a sample from Tullamore where we looked at the heat demand and Pablo calculated there's potentially 100 times the heat demand of Tullamore in the ground beneath Tullamore down to, I think, about 800 meters or 900 meters or something like that. And then, of course, the other piece with this is the cost and economics. You know, you need to be able to tell people, well, you're going to get 6 megawatts. It's going to cost you 17 million, and it'll drop your CO2 by, you know, you'll save 140 tons of CO2 per year, or over the lifetime of the project, because that's what's going to matter to people. So that's the key thing is you can translate it into what people's problems are once you take that step. If you just hand them data they don't necessarily understand that. And it's important to sort of come up with the headline numbers from that. But as Kuhn said earlier, when people can touch stuff or see something, it makes a big difference. And that's why in Work Package 4, Work Package 5 is really about the actual generating data and doing activity. We've just, Kuhn was talking about sticking fingers in the side earlier in the holes. This is core that came out of the well we've just finished drilling in Tullamore. Again, the reason we're drilling with Tullamore is because we engaged with Tullamore County Council, saw that they were progressive, interested in geothermal. It was an area we found an interesting location on a kind of a fall panel to drill, and we saw good temperatures in Grange Gorman when we drilled. This is the first time we've actually seen porosity in a well. We've actually seen open fractures at depths of 800 meters. So it's given us another indication. Actually, some of these systems work well and could work it. The critical thing with that is when it comes to those drilling programs that we look, can we get all the information that we need from them? These particular ones, it's a sort of mining rig. We can't drill the holes in a way that you can do, let's say, a flow test or a pump test on them. If you moved up a scale in rig size, you could potentially do much bigger data gathering wells to go along with the seismic data, do VSPs, things like that they're going to calibrate it. So again, we looked at that district heating map, came up with 10 sort of strategic locations from a geology perspective and a district heating perspective, and cost engineered a well, designed a sort of a standard well bore and costed it up, so we know how much that is going to cost. Key with this as well is that it's integrating back into internal stakeholders and things like district heating. There's many ways which geothermal could impact district heating, from direct supply, the traditional thing, to low temperature ones. And again, when you do these activities, you drill these wells, we're designing a seismic shoot for Dublin at the moment. If that's to go ahead, you can bring those stakeholders with and say, look, this is actually a real thing, we're doing it. And so ultimately, what we've come up with, Kuhn said it earlier, he has got a line apparently on money where people want to invest in big things. So what we've done essentially in this part of the project is actually cost up what a program like that would look at, tie it into a national level strategic direction, which is district heating and heat decarbonisation, and also looked at some of the key economic metrics to say actually it's worth the money. And so what we think will get us certainly off the ground is a regional 2D seismic program of about 10 million that would cover probably about 2/3 or more of those 58 district heating locations. Maybe 10 to 12 of those regional deep temperature wells where we can get not only the temperature but some of the seismic VSP data, flow tests, and then a couple of million for a national lab that we can start to build up the repertoire of those core-derived log suites. Of course, you need money as well for people to actually do the work. At the next stage, so this is the regional level, at the screening level, an urban 3D seismic, if you find something on the 2D or a prospect, that's going to be one that needs to be done. The deep open loop and testing is something that obviously through the Gemini project we're going to do, but there might be other locations. After that, maybe 3 pilots, large scale pilots, 10 targeting stuff like 10 megawatts of heat for about 60 million. And that's all that's sort of, let's say, more on the open loop side, where we know the technology is already proven. It's just a matter of trying to get it done at a scale to tackle the projects that we're already, basically material projects that you can use to say, look, this is making a difference and it's easily doable. So all in all, you're looking at maybe 120 million there. For reference, Ireland has done a very good job of wind. Wind is about 1.8 billion of public money put into it to get where it is now. So we're talking about not even 10% of what has been put into wind. And heat in Ireland is as big an emissions problem as electricity. So I don't think this is a big ask. I think it's one that we've already shown we can do a lot with very little in geothermal. So I think this is one that, we'll definitely going to keep pushing around till we get some money for it. So I have another slide on research things, but
leave it there. I think.
Our last speaker is Vincent, and he is going to talk about, again, the National Geothermal Database.
All right, thanks. Last talk. So I'm Vincent Roche from UCD, and I'm going to talk again about the National Geothermal Database following the introduction by Rory, but here I'm going to show some more technical detail of what we've been doing on the side of the Basin-scale structural modeling for de-risking the geothermal assessment in Norden. Okay, so my introduction, we talked about that all day, so I'm going to go fast as well. Geothermal systems are influenced by the depth and the characteristic of the geological formation with different type of resources available depending on the amount of recoverable heat. And in this project, the National Geothermal Database Project, we aim to reduce the risk in geothermal exploration by providing subsurface data, including the location and the depth of the reservoir, the information on the plate type, and the resources available. And for that, we aim to deliver maps and 3D geological models that could be open source for stakeholders to de-risk their geothermal resources. So I started to work in this project a few months ago, and this is a team effort. And so here you can see some of the people that contribute to what I'm going to show here, including Pablo, which is somewhere here as well, and some of the other people as well. Okay, so this is a very cool color, but you can see here the simplified geological map of the solid rock of Ireland. It's better on this side, I guess. And so you can see that most of a large part of Ireland is covered with carboniferous rock, which are sedimentary rock. They are supposed to be in blue in there, but better and those are mostly carbonates. And those rocks have been identified as potential targets for geothermal resources in Ireland, but also they are equivalent in UK, they are equivalent in Belgium and in Netherlands. And in the map here, you can see, so this is this area, and this is from the PhD thesis of Robert Doyle from ICRAG, and you can see that those carboniferous rocks are faulted with the faults that Robert interpreted here with those lines, with some north-dipping faults, south-dipping faults, a lot of different faults. And those faults mostly have a normal movement, so we're going to have this kind of geometry here, although some of them are also reactivated, like some of the examples we saw this morning in the talk by Pat Meere. And so we are dealing here with a faulted basin, basically. That's what I would say. And in this case, the fault will play a key role in controlling the depth of our reservoir. You can have an eye on the footwall, a low in the hanging wall. This is also going to control the thickness and the property of our reservoir, especially if you have a growth sequence associated with this fault, which we have in some of those for some of those faults. And also we're going to control the fluid flow either through juxtaposition or along fluid flow by increasing the permeability of the fault. Okay, so all this to say that this defining the subsurface fault geometry and their movements is very important for all those reasons to assess our geothermal resources and the risk associated with the geothermal assessments. Okay, and so this is what we try to do in this project, defining the subsurface geometry of this fault movement, and for that we integrated a wide range of data that are available. And the first type of data we integrated are a large amount of well, which we are actually very lucky to have in Ireland, mostly due to mineral exploration. So we had some people in ICRAG collating all these wells, giving us a large database. We have more than 27 formation tops that we've been using to constrain our subsurface geology. as well as the stratigraphic correlation across the basin. So that's our first type of data. Then we also have the 2D seismic line. You can see here the trace that we used so far, and you can see an example of an interpretation of a portion of one of the seismic lines. This is from Kuhn Thomas from UCD. And you can see here some of those normal folds offsetting the Carboniferous basin. And this is a very nice line because you can clearly see here for geothermal resources, if you have to drill and one of those rocks is your reservoir here, you can see that here it's going to be pretty good, here maybe okay, and here not so good. So you really want to know where you are relative to those faults in order to de-risk your geothermal resources. Okay, then we also use geophysical data, electromagnetic, magnetotelluric, gravity, all the type of data that are available in iCRAG. This is the airborne TELUS data. We use that mostly to try to have an idea of the trend of the subsurface structure when we don't have any other type of data. And finally, we also use the surface geology, the 50K geology map from GSI, as well as all the previous structural geology work that have been done, such as the work by Johnson 1999, or some of the fault model by Meritzman in 2002, as well as more recent work by iCRAG. So I just showed a regional analysis by Robert Doyle, but also all the very nice detailed 3D model of the mine that has been done by Kuhn and by Roche in iCRAG in different positions across the basin. And so we're going to integrate all those data to try to build our subsurface 3D model. Okay, so to do that, for example, if we use the well, we can identify where are the faults by just looking at the depth of the different top, as well as the thickness of the layers. And so we can identify the fault like this. However, because the data are discrete and are not homogeneously distributed, we're going to have quite a lot of uncertainty in what's going on between the data. And also there will be some area where we don't have a lot of data. And also if we were to build an horizon just by interpolating those data points across the area that we want to do, this will result in unrealistic geometry. We will have an horizon that will smooth the fault, with the smoothing that will depend on the density of our data. Okay, and this will generate a lot of uncertainty in where our geothermal resources. So in order to avoid that, we use a different approach from structural geology, where basically what we're going to do is we're going to build what we call the cutoff of the faults, which are those yellowish orange line here, which represent the intersection of our horizon with the fault surface, which is here in red. And then once we have this cutoff, we can use this cutoff as well as our anchor point from the well to build a more realistic geometry of our horizon, where we're going to have the displacements on the fault that is continuous, looks like what we expect, and the depth of the horizon that is controlled by these faults. Okay, and one thing that is important to do that is that we can do that because we have been, in the fault analysis group, we have been looking at a lot of these cutoff geometry by looking at auto-tracked horizon from high-quality 3D seismic data. And so that knowledge is actually important in order to build those realistic cutoff geometry. Okay, so that's where we are right now. So this is the faults that we mapped so far, and this is the area that we did so far. So this is 150 faults. This is going from Longford to Kilkenny, Dublin to Limerick. So this is quite a big area. You see here the faults are in 3D. This is a 3D fault surface. The red are dipping south and the blue are dipping north. And here you can see the cutoff geometry associated with all those faults. Now, building this cutoff geometry is actually quite a complex process and takes a lot of time. So for this project, we decided to only do that for one horizon, which is going to be the top Palestine formation. And we decided to use that horizon because it has a lot of lateral continuity in the basin, and it's well defined by the data. But later I will show you how we can still use that reference horizon that we're going to build with that to build the entire 3D model. Okay, so then once we have our cutoff, we can build a 3D horizon with our cutoff and with the anchor point from the well. And this is the top Palestine horizon you can see here. So the color, so this is in 3D, the color represent the elevation. In blue, it's the low in the basin, and in red, it's the high in the basin. And so what you can see is that we can see very clearly all the faults that we mapped and that control the depth of the horizon, forming this nice fault block. And from a structural geology perspective, this looks like a relatively realistic horizon. This is the kind of stuff you're going to get if you do auto tracking in offshore island, Porcupine Basin, or in the North Sea, for example. And this is again like a relatively large area. Okay, so if we look a bit at that horizon now, so this is our horizon, and here you can see a simplified map of the fault that we identified with the main faults. And here, what was supposed to be in red, but I think it can be gray here. I'm colorblind, so I cannot really tell. Are the basin low, which will be potentially the best area for our geothermal resources. And so you can see that here on the eastern part of our model, we have some low associated with these faults here. We form some kind of a graben geometry. Then east of Mullingar, we have this half graben geometry forming some quite nice low as well. Then we got the large Dublin Basin, which is quite low, with the fault that John was talking, the Black Rock fault / Oath splay. Then you can see that this low split in two, one that go all the way to Tullamore, as we recently saw by drilling in this area. This is still quite deep there. And then in the south, going all the way to the Rathbone Trent, and in the middle, the Schlickby. We also have a low potentially below the Castelcomer Plateau, and then some low on the west associated with this large north dipping fault. Okay, interestingly, what we can see is that if we look at the eastern part of the model, the low are mostly controlled by some large south dipping faults. While if you look at the western part, the low are mostly controlled by some north dipping faults. And so what we think is going on is that we have this kind of change in the distribution of the polarity of the displacement on the fault between the north and the south dipping fault. So we have a change in the polarity in our basin. And this is the kind of geometry that we expect. This is modified from John there. And this is also sometimes called a convergent transfer zone. This is something you can see in many other basins. Okay, so that was for just our reference horizon. But still now I'm going to show you how we build our 3D model out of that. So, and for that we are using the sort of Petrel. We have our reference horizon here, the top Palestine. So that's the same as I was showing before. Then we imported our faults the fault framework. Then we also imported our well, and we can calculate some thickness map for the different formation we want to model. And then we put all that together, and we can build the structural model where all those horizons here will take into account both the displacements that we model for our reference horizon, as well as the thickness change between the different formations. So we have a full 3D model here of the Carboniferous Basin, and then we can build a 3D grid here for different formation, going here from the Calp or the Lucan formation down to the old red sandstone. Okay, so we have a 3D model, and then once we have a 3D model, we can add property to the model cells. And this is something that Pablo has been doing, and we can use that to calculate the resources available.
And for that, we use the method of the heat in place. And here are some of the equations we are using. So first, we are calculating the stored energy H0, which depends on the volume of the cell, the porosity, the density, the heat capacity, and the temperature of the cells. And that stored energy basically represents the resources, the heat that is available in the rock. And then we can calculate the extractable energy, which is basically that stored energy multiplied by a recovery factor R, which is going to take into account the technological limitation of the heat we can extract, as well as the property of the reservoir, whether it's good or bad reservoirs. And okay, so then you can see the final result here. You can see the stored energy here. So this is now a map view where we integrated all the heat vertically, and you can see in red, orange, the different hotspots in the basin where we will have the most resources. Now, this doesn't mean that the blue and the more bluish area are not suitable for geothermal resources, but it just means that it will be more for shallow resources. And then here you can see the extractable energy. So far, we just apply basically 5% of the stored energy, but in the future, we aim to use a more refined method where we're going to account, for example, for the quality of the reservoir due to secondary fracturing, due to the presence of large faults, taking into account the movement of the faults. And the idea then would be to directly compare this recoverable energy with, for example, the heat demand in Ireland, and see how much the geothermal energy can account in your heat or energy mix, for example, for any stakeholders. Okay, so that was me. Conclusion: Ireland possesses a unique suite of data and expertise for reducing geothermal exploration risk. I mean, we are quite lucky to have all those well data for the mineral exploration, and we're ready to leverage that. We also have expertise from people that have been working in basin analysis for several years, so we can use all that to reduce the geothermal risk, geothermal exploration risk. Nevertheless, reliable data is always essential for de-risking the subsurface geothermal assessment, and I think the kind of work we are doing is key to have informed decision to identify where are the gaps for our data. And at the stage where we are, we can already say, where we need the data. And I think the Tullamore example, was a good example of, having some of those interesting data in one of the areas where we actually had a gap. Structural geology knowledge that we have in Ireland is also can help for advancing the geothermal project and dealing with onshore data, which are not necessarily the quality that we could expect for building this kind of 3D model. And so in future work, we also aim to expand the subsurface model to additional areas. So in particular from the Dublin Basin, and maybe going all the way to Galway if we feel like we want to do that. Then we also want to refine the geothermal recovery potential through, by better integrating the faults and fracture analysis. So that's the second part. And then enhance maybe the model for strategic and high demand region to optimize geothermal resources use. And so that was me. Thank you for your attention. And then again, thanks for the people already involved in this project.
Yeah, I would have to take all the dias in Eva and on organizing this, and also our IT guys as well. Thank you.